to have the first session of today, which are two plenary lectures by Professor Anton Duplessis and Sir Klaus Pedersen. For the first talk, the title is Fatigue of Gyroid Lattice Structures of Ti-64, produced by laser powder bed fusion. The duration is approximately 40 minutes. And after the presentation, you're welcome to ask your questions. You can either raise your hand or write your question in the chat. Anton, if you're ready for the presentation.
Perfect.
Yeah.
Thank you. Thank you very much, Mr. Chairman. It's great to be here. Let me just start the presentation mode. So I'm quite excited to be presenting my work to you today. I will be talking about fatigue of gyroid lattice structures by laser powder bed fusion. But actually, I will also take the opportunity to present a broad scope of my works from the recent years, which lead up to interpreting some of our experimental results from this work. So I hope you find this interesting. My name is Anton Duplessis, and I'm from Stellenbosch University, South Africa. My work is partially funded by the collaborative program in additive manufacturing, ESIAM, which I'm thankful for. And my group is called Research Group 3D Innovation. So before I start, I have two announcements I'd like to make at this on this forum. And the first one is about the Elsevier Journal Additive Manufacturing Letters, which we have launched this year. If you are not aware of it yet, I'm glad that I can share this with you now. It's a short format journal associated with a big additive manufacturing journal, which I don't know if everybody is aware, it has reached, and the big journal has reached an impact factor of 11 at the moment and is rated #1 in the category for all manufacturing journals. So this journal is meant for short format, really high quality papers, almost ready for publication, and therefore with a single review cycle, it's possible to publish your work in a short time. So that's the one thing. Oh, and at this position also, I want to say, if you are not being asked to review papers, please get in touch. And if you are willing to do that, I'm always looking for more reviewers for the work and to improve the quality of papers. So it's good to get a wide variety of reviewers. So please don't be shy and get in touch if you would like to review for either of these journals. So the second announcement is about a book that we have completed and published this year, Fundamentals of Laser Powder Bed Fusion of Metals, also called Selective Laser Melting. Actually, the correct term is laser powder bed fusion, and please, we should continue to use this term and not SLM anymore. This book was actually written 24 chapters by different authors from all over the world, more than 50 authors. It's really a great collection of work and a reference work that can be useful for students, for teaching, or actually more wider than just laser powder bed fusion. Many of the concepts are relevant to all metal additives. And I invite you to check that out. It's the first 4 chapters are free to view and read in Google Books previews. So with that, in this talk, I'm going to try and stick to the time. I'm going to actually, as I said, present a variety of things. A lot of the time is spent on the first point, where I'm looking into metal AM in bulk material properties, and particularly the effect of defects. And I use X-ray CT in this, non-destructive imaging of defects before and after mechanical testing, which is something that I've would like to present in a bit of detail and how that can be useful. Then I will move on to the motivation for why we are interested in lattice structures or cellular structures. And I will present some work that we have completed in this direction, looking at the influence of defects on the performance of such structures, and some very recent work on different densities of gyroid lattice structures with extensive fatigue test results. So some of the bulk material properties, effect of defect, conclusions are actually used to interpret some of the results of the fatigue and the gyroid mechanical testing in general. So just to put that together. So we are talking about metal additive manufacturing here, and as a bit of a motivation for that, the reason we are having this conference is we want to improve the properties of these materials in order to make possible real industrial applications. One of the early adopters is the aerospace industry, and I'm very happy with this review paper which we published this year. It's open access, so you're free to read it and check it out. It's quite an extensive review of all successful cases in aerospace of interesting applications and areas where metal additive has an advantage compared to traditional manufacturing methods. So taken from this work is a table listing all the popular metal alloys used in aerospace. This list is continuously growing, and of course it's also possible to create new alloys by mixing powders in powder bed fusion processes, for example, also called in situ alloying. The reason I show this is that each one of these materials need to be optimized, and we need to investigate their properties in detail, and that is where we are interested in making sure we obtain great material properties from all of these alloys. So if I were to make a summary of the properties of metal additive manufactured components compared to traditional parts, they have unique microstructures, residual stress, especially in laser powder bed fusion processes, unique porosity contents, which can vary a lot and which has been recognized in recent years more widely, and of course the rough surfaces. So all of these influence the mechanical performance of components on different performances, not only mechanical, and the relative importance of each of these surfaces, the extent of roughness, extent of porosity, and the extent of all these features are influenced strongly by a wide variety of parameters. As you know, this is a summary, so many of you know this, but the laser power, the scan speed, the head spacing, all of this influences the propensity or the chance of porosity formation, the roughness forming on the surface, and the residual stress forming, and so on. So even there are scan strategies, and many of these things are also interrelated. So it's a really complicated process to optimize, and for this reason, there's a wide variety of performance that has been reported. Some of these go unnoticed, some of these influences. So some which I will mention later in some of the results is the end of track scanner of situation for each system can vary. Some systems use skywriting, which is shuttering the laser off at the end of a track, whereas some systems slow down and turn around, which can influence porosity formation in particular at that location. And then of course the powder size and shape influences the powder bed packing density. There can also be porosity inside powders, inside gas atomized powders. Pores can be in the powder itself, which can then transfer into the melt pool. This has been proven in different studies and can be trapped there during solidification. There's also contamination and oxidation of powders that can take place. The gas environment influences the properties of the parts produced. Preheating influences particularly residual stress, but can also influence the powders surrounding it, and so on. So it's a really complicated situation. And one of the ways to evaluate the properties is using cross sections or CT scans. So I use X-ray tomography or CT scans a lot in my work. So I'd like to just present a couple of slides on that. Schematic is shown here where the X-ray source shines a beam of X-rays through an object. You image the object in you get an X-ray projection image. Then you rotate the sample and get thousands of projection images, which are then used to reconstruct a 3D voxel grid of data, which is a representation of the density and atomic mass of the object at each point in space. So you can, with this data, make cross sections similar to physical cross sections, but in any orientation. And you have full 3D data, so you can make more advanced analysis. The best way to explain this really is with a video. So this video shows a grid of data of pixels, the black pixels being air and the white and gray pixels being material. By removing the air pixels, a process called segmentation, you can remove the part from the background, and you can then evaluate this. This is a light metal casting, and we can evaluate, in this case, the porosity inside, and evaluate where this porosity sits exactly, and also more advanced analysis is possible, like wall thickness analysis and so on. So this is the benefit, and the particular benefit is the non-destructive nature, which can be beneficial for mechanical testing subsequent to CT scanning. So I've just shown you a casting, and I'd like to use that example to move to porosity evaluation and show you how in cast metals, porosity occurs in many materials, and also in, not only in additive, there's a lot of talk about porosity in additive manufactured parts, but actually there's a lot of porosity in all kinds of materials, especially cast metals. As you see here, particularly, I'd like to highlight the two columns here, where on the left is shrinkage porosity with a very irregular shape, and on the right is gas porosity, which is due to a different mechanism in the casting process and has a more rounded shape. So this is very similar in terms of different mechanisms leading to different pore morphologies and distributions. The same kind of thing happens in laser powder bed fusion, where all of us know already about lack of fusion and keyhole porosity forming due to different physical processes or mechanisms, and different things happening in the process. And in CT scans, what you've seen were cross sections, and these are now CT scans of small cubes of material with intentionally produced lack of fusion and keyhole pores. So it looks quite extensive because it's now all over the part, and you can just use a pointer here. So it looks quite extensive. It's only in the level of about 0.5%, but looking at it in 3 dimensions, it looks quite a lot. A cross section looks similar to a physical cross section with black dots representing pores. And if you then highlight one of these in 3 dimensions, you see the lack of fusion is very irregular and elongated, and the keyhole pore is more rounded in shape. So it's not only CT which has helped us in the recent years to understand pore formation. Actually, there have been some great studies from high-speed synchrotron X-ray imaging. This is one of such studies where they've investigated different variations of pore formation mechanisms. The image sequence shown here is a keyhole formation, where the vapor cavity is unstable as the melt pool moves towards the right, and the keyhole breaks off at the tip and leaving a pore in the solidified material. So many different variations of pore formation mechanisms have been identified in this way, and I'm not going to go into all these different mechanisms. I invite you to check the book that I've mentioned before, where this is discussed in more detail. The point I want to make here is that it's not a simple case of lack of fusion and keyhole porosity. There are different variations of this and different combinations and different things which cause situations for different variants of it. So one way to understand this a little bit better is to intentionally induce such situations. This is a study of 2 years ago already, where this was done, and I demonstrate this here because we've done a similar thing with the lattice structures later, where we've kept all parameters constant and varied the laser power. So having a low laser power with a fixed scan speed allows you to generate a lack of fusion porosity, as you see on the left top there, and this decreases to C and D levels there, where you have very low levels of porosity, and then gradually keyhole pores form more often in the material as the power increases. So this was studied actually at different scan speeds, and in this case we find at the higher scan speed the optimal level is having lower porosity than at slower scan speeds. But the point is really that we can induce these pores to understand their formation better and to find the sweet spot, the window of good parameters that can be used. Something which is quite often found in AM parts is a contour porosity just under the surface. This is an interesting phenomenon where different mechanisms can cause this. One can be induced quite easily by changing the contour and hatch spacing. So the overlap between the hatch tracks and the contour tracks can be made wider to induce a kind of a variant of lack of fusion porosity. There are also other mechanisms which can be causing this. In some systems, as I mentioned, the laser slows down towards the end of the track, causing keyhole porosity to be formed at those positions as the melt pool penetration is deeper and there's more of a chance of unstable cavity formation there. And then in some cases, it has been shown using high-speed X-ray imaging that small pores can be trapped in the melt pool, melt pool flow and trapped and while it's moving along. So it captures pores, entrapped pores which move along with the melt pool, and at the end of the track, they are left there. So this is quite important for fatigue performance. We don't want pores right near the surface because this causes track initiation locations. So moving to surface roughness, the possibility of cross-sectioning parts and using CT scans to evaluate this in detail. I think this is something which has recently only been investigated in enough detail because many of these features can be easily missed by tactile probe measurements or by surface imaging techniques. Some examples are shown here in a cross-section where the white represents the surface. You have a kind of an undercut in this location, and you have some deep surface notches or notch-like features, which are quite important to know about and understand. So similar to the previous work I've shown you where the parameters are changed, actually the same exact samples where the laser power is increased, 280 watts is the minimized porosity value. We can quite easily evaluate the vertical side surfaces for roughness. What we see here is not much change, and to save time, I'm not going to go into details here. Interesting that the highest power has less attached particles, but generally the surface is reasonably similar except for the amount of attached particles. What is interesting is we've made one sample with the same parameters, 280 watts, the optimized parameters, but without contour track scanning, which then creates clearly a lot more blue features, which is negative, which are surface depressions. This is quite important to know about and is a clear example of how contour track scanning improves the surface. This is for a vertical side surface, and what we see is quite deep surface depressions, which were not visible in any of the parameter sets with contour track scanning. So this is quite important, and as I said, this is actually used to interpret some of the results we found later as we made some gyroid samples without contour track scanning as well. So it's not only the process parameters, but also the overhang angles in the build process, which affect the roughness, as you can quite easily see in this color-coded image here, where the red indicates higher excess material and blue showing depressions in the surface. So this is from a different study, but just to show the different inclination angles, and this is quite important for lattices as all cellular or lattice structures and all complex parts manufactured have different overhang angles. So it's something to be aware of. Also, just an interesting result from the study was that the roughness and porosity are sometimes related to each other. On the left is the bottom down facing the down skin surface, which has some porosity associated with it just under surface, and at the top surface, slightly better quality than the bottom surface, but in this case, having quite extensive lack of fusion just below it. So this has been published, but I'm not going to go into detail here. The point is just to show that it's important to understand the parameters and to understand how to improve this and minimize the extent of the roughness, and the porosity. This is a cross-section from the same work. The point is really that for each process and each material, this has to be optimized, and it's not possible to have a generic answer of fixed parameters set for any, even just for one material. Each powder material, each system, additive manufactured system used needs to be optimized in order to achieve good performance. So in order to achieve good performance, what is defined as good performance? We need to evaluate the effect of these imperfections that occur, the effect of defects on the performance, in order to understand what a safe zone is and what is a good process. So in order to understand the effects of defects, it can be useful to use non-destructive imaging of the defects before and after mechanical tests. A very simple example is a tensile bar shown here. This is from a couple of years ago already, where we used casting tensile bars, cast metal with quite large pores of almost 5 millimeters in length. And it's quite a nice demonstration showing where that the failure in a tensile test occurs at the largest pore in almost all cases, irrespective of the microstructure in that case actually. And it's also possible to make simulations on the CT data and evaluate the stress concentrations alongside the pores. So in additive manufactured materials, of course, the pores are much smaller. This is one interesting result where the pores were very small and evenly distributed, something like 0.01% per volume of porosity, less than 30 microns. So of course, the stress concentrations are not so high in that case. But what we did find, which is interesting, was in the necking region. So this was the same sample before and after. This is at 9% elongation for Ti 64 as well. In the necking region, some pores become visible, which were not visible before. So in this case, the process of evaluating the same sample before and after testing helped us to understand that this, what is happening here is pore coalescence. So pores were becoming visible above the scan resolution due to the pore coalescence occurring. So same thing can be done in fatigue tests, and this is a study where we evaluated the surface condition for different orientations of build directions, trying to correlate before and after CT scans of the same object with evaluating the location of crack formation compared to the surface features. You see very nicely in this image here, where the red indicates the surface depression in the highest stress region in the middle of the sample. This is where the crack initiates and propagates to 1 millimeter in this case. So in the study, we tried to identify which of the surface features in additive as-built surface condition act as the killer notches or the effective crack initiation locations. So in order to explain that, I've got a nice video. I just can change from laser pointer here. So this is the worst surface condition evaluated in that study. And with a contour color map, again, we can evaluate where just to emphasize, the evaluation of the surface is done before fatigue testing, and then the after tested sample is overlapped with this data, and the crack is highlighted in red in the post-process data, and the overlap shows very nicely where the crack initiates and is located in the high stress region, but also correlated with the deepest depression in the surface. So it's not only the surface condition that is important. From the same work, it was also seen in some samples that cracks propagate through pores. In this case, we have some contour pores, and the crack passed right through the middle of one of these. So this is for interest, just to explain that both of these are quite important. Okay, so moving to the topic of the talk really, which is lattice structures, and now I have only less than half of the time for this. I want to highlight this review paper, which I'm quite proud of, which we completed this year, and it's also open access, so you're also free to read it. There's a lot of interest in utilizing the complexity of additive manufacturing, and especially metal additive manufacturing. And cellular structures or lattice structures are one of the most complex design principles, or one of the most complex types of structures, which have quite unique properties and unique application potential. One of the big concerns is the mechanical properties of these structures, and especially the fatigue performance. Basically, you sit with a structure with many stress concentrations and effective notches just by design. So it's quite important to understand how to optimize these and which geometries are suitable for fatigue applications, and how can we improve on these properties. So in terms of motivating for this work, applications, there are many unique applications. One of the most obvious one is lightweighting. So you can generate light-weighted structures utilizing much less material. And this is an example of an automotive bracket for a student project at Nelson Mandela University in South Africa. And this is an example of a more commercial accepted application. These are hip and knee implants produced commercially in South Africa at Executive Engineering is the company. They use laser powder bed fusion to produce these implants with some lattice structures on the surface. The aim of that is to reduce stress shielding and to allow bone ingrowth. And this is done commercially, and it's an accepted application already. So in terms of introduction of cellular materials or lattice structures, porous materials occur in nature because of their unique properties and especially the minimized material usage for a particular application, but also the multifunctionality in terms of allowing permeability, or in the case of bone structure, allowing vascularization through the cavities, and also there's some mechanical advantages in human bones. I'm not going to go into too much details of the application side, but more as a motivation, you can see the trabecular bone structures looks very much similar to gyroid structures, and that is one of the motivations for investigating this particular structure. The cellular beehive honeycomb structure is already well known. It's called a 2.5 dimensional structure, but also has found some applications already in that case, especially in the high surface area. So for heat exchangers and also for impact protection applications. So of course, for additive manufacturing, there's a wide scope of designs that can be utilized. These are examples of the different styles of unit cells that can be used. Strut-based lattices are most well known, where you have beams connected by, or struts connected by, at nodes, and in different architectures, each one having particular different properties. And then we have triply periodic minimal surfaces, which are increasingly popular. There are two styles of this, the sheet-based at the bottom and the skeletal design. We are using the skeletal gyroid in our work because for the same design density, we have a thicker material wall thickness, which makes good manufacturability compared to sheet-based or strut-based versions. The other advantage is also that it has homogeneous thickness across the entire structure. So with struts and nodes, you have different thicknesses at different heights. And with sheet-based structures, you all have similar. With these structures, you have the same thickness all over the structure. So first experimental data that I would like to share here is about, similar to the previous examples I've shown you, we've intentionally created microporosity inside the material by varying the laser power, and changed the condition of the material by intentionally creating defects and then investigating the influence of these defects on the mechanical properties. So of course, I used CT scans, and I have a nice video to show that for that. This video shows in green, this is a 20 millimeter wide sample with in green showing all areas within 40 microns of the design, confirming that the manufacturability is quite high for these structures. The red regions as we fly through the structure shows some excess material at the down-facing surfaces. But in general, very, very well designed structure, very well manufactured structure. So just to show the experiment here, the experimental results, we've used CT scans to measure the porosity intentionally produced from 100 watts all the way up to 360 watts, where the control is at 280 watts. And we made a special parameter set in addition, which creates a lot of lack of fusion, similar to the 100 watts. And then a no contour example where it's a control sample, but without contour track scanning. So as I've shown you earlier, the contours improve the surface. So in this case, the surface quality is worse, and we were interested to see how that influences the performance of the structures. This is just a zoom in on that. Basically, the quasi-static compressive strength or the yield strength increased as the laser power increases up to beyond 250 and 300 watts. We have pretty much similar good yield strength. Obviously, lack of fusion does influence that. And the special contour, which was also a lack of fusion condition, also influenced that. Interesting to see that the no contour one is with the uglier surface condition is also influenced a little bit. And that is interesting to note. In fatigue tests, we've used quite high loads in these fatigue tests in order to save time and to highlight differences. What we've seen at the lack of fusion, we've used 70% of the yield strength of each case. And we see that at lack of fusion, we have very, very few cycles, low life, and this increases up to from 250 to 360 watts. And for the control sample, we have quite relatively good and constant life achieved there. Interesting, the drop for the sample with no contours, almost a 25% drop in life there. So in the same set of experiments, we've also done hot isostatic pressing, which is an interesting and great process. The interesting result here, despite lack of sample numbers, because numbers were lost during the high temperature process. The interesting result here, if we compare to the previous slide, we've had for this optimized parameters here, 44,000 cycles. At many of these samples, we had more than 100,000 cycles, up to 1 million cycles achieved for the same load ratio and for the same load used. And the interesting thing is here that the performance improves in many of them, but not in all. So these 4 on the left were actually reduced. These were less than 1,000 cycles. And we can explain that by understanding the hot isostatic pressing conditions. We've investigated this in quite some detail before, and it's a great process to close pores and improve the microstructure. The only point is really that surface connected pores like this one is not closed. So when the gas can penetrate the pore, it's not closing the pore. The interesting thing here, and what I want to mention at that point is it's a great process to close pores, but it's not meant to close, to correct for bad process parameters. So the ideal situation is to have an optimized process and then apply HIP to that, because you will always have near surface pores which are somehow connected to the surface, and therefore, even though there's 99.9% pore closure, it's still leaving some pores near the surface. The most important thing I want to highlight here is that we found what you see here is the same cube before and after, perfectly aligned. And what you see is a small pore near the surface there. This particular pore was actually pierced open and leaving an ugly notch-like effect on the surface. This is what we think happened in the case of our extensive lack of fusion samples in the gyroids, where the ugly pores near surface were pierced open in the heaping process, reducing the performance of these samples. So finally, I've only got a few more minutes, but this is quite interesting recent work, not been published yet. We stick with the gyroids and we then create samples with 50% on the right, 37%, 25% and 12% density. With the same unit cell size, this allows us to have effective wall thickness or strut thickness varying from 0.6 to 1.8 millimeters. So this can give us some insight into how thick lattice structures should be in order to achieve good performance. And the aim here was to get the best possible fatigue performance. So we expect the thickest struts to perform the best. And this is what a full build plate of such samples looks like, manufactured in this case at the Central University of Technology in Bloemfontein, South Africa. We've used stress relief before removing them from the build plate and annealing at 940 degrees for 2 hours, because this material and process and combination with heat treatment gives us up to, in traditional quasi-static tensile testing, up to 15% elongation with more than 800 megapascal yield strength. So we've used these samples for a series of fatigue tests, and we've also applied a load simulation to such a full lattice structure. Without going into details, you can see some stress concentration areas on imperfections on the surface here, the red areas, but the pore space that you see in this one cropped open view is actually not contributing to that. So this, as the lattice structure becomes less dense, the surface becomes more important. And in quasi-static compression tests, we find that, as expected, the 50%, the densest sample, is the stiffest with the highest yield strength. We've just used this to evaluate, to define the conditions for the fatigue test. And just as a final exciting result, I've got this SN curves here for all these samples, with 50% samples having 2 run-out samples actually at 2 million cycles, which is very nice. I have to mention that the stress values are calculated based on the actual area of the material. So this should actually be scaled further, and then the differences between these actually become even worse. So these samples, these curves move downwards, but quite a good performance and run out at quite high values. So reasonably successful and quite exciting. So I'm not going to run through some of these conclusions. My time is almost up, but I hope I've shown you some interesting results here on effect of defect studies and how this can help us to understand performance and which defect types are most critical. The contouring is quite important, improves both static and fatigue performance in the lattice structures at least. The HIP is a great process, and what I want to emphasize on that is that we need initially low porosity for it to be most effective. So it's not a way to improve a poor quality part. You need an optimized part and then apply this. So good fatigue performance can be achieved for these gyroids, and watch the space, because we've also performed hipping on these last sequence of samples, and these experiments are almost completed. So if you're interested in my work, please get in touch or connect with me and follow me on LinkedIn. Thanks a lot for your attention. I'm open to questions. Thank you.
Thank you very much, Anton. It was a nice presentation and quite broad topic you covered in this presentation. Thank you.
Thank you.
From the audience, yes, Professor Stampo.
Yeah, so first, thanks for this very broad and very interesting presentation. As you showed, the challenge might be these internal and external notches, which we typically have in layered manufacturing. And especially with regular structures, you might easily get localization of damage. So did you also look into somehow put in some randomness into these cellular structures to avoid localization in damage?
No, we've not done that, but it's a good point. And what we aim to investigate is what the influence and the relative importance of different defect types are. And if you have an incorrect process parameter set, these defects do occur all over generally. But of course, there are other, there are some defect types which can occur in particular layers, which are quite important. So there's a lot of work that still remains to be done And we hope we make progress in this, but it's a good point. Thank you.
Thanks.
There is another question from Giovanni Bruno. He's asking whether in the numerical simulation, they were performed in purely elastic condition.
I'm here.
Yes.
Yeah.
Yes. So let me just try to go back there. This is not.
Yeah, the point, Anton, is that the nonlinear behavior is very difficult to simulate.
Yeah.
And
definitely.
of course, the elastic region is easy or too easy. Of course, this the correlation is good. Yet you see the point is to get what happens afterwards.
So this is definitely quite interesting and something for the future. As computing power has increased in recent years, it's possible to take such data from including all this detailed surface information. Remember, this is not the only part of the model simulated. This is one unit cell of a 5 by 5 by 5 structure. So it's really quite a big model, but it is possible to simulate this non-linearly and to follow this non-linearly also, including deformation and things, which is quite exciting. And I'd like to do more of that, but we need some, in that case, definitely some collaborations with experts in numerical modeling.
Thank you.
The next question is from Professor Kian.
Yeah, thank you. Thank you very much for your very comprehensive and very interesting talk. So I'm quite interested on the effect of hot isostatic pressing on the porosity and also on the mechanical property. So you said that this hot isostatic pressing can reduce the porosity and also increase the mechanical property. Also, some other work also reported that somehow, because of the pressing, some gas pore inside the material could be broken and also can somehow increase the stress concentration, and then therefore mechanical property could also might be decreasing. So I'm not sure whether you have also some kind of these observations.
Yeah, so it's a great process which I've been investigating for a number of years. If you remember this casting sample I showed with 5 millimeter pore, we've subjected those samples to hipping 5 years ago already when we just started, and I was amazed that it was closing up this entire pore to below 10 microns, which is quite amazing. And I think there's some misunderstandings about the process, which is why we've investigated it in quite some detail in this one paper I've shown you there, where basically surface connected pores cannot be closed, and if there are connections of pores, if there's a number of lack of fusion pores connected to the surface the gas can pierce those connections, which is basically what you have seen on one small keyhole pore now. But I think that basically confirms what I have said is that the method only works, hipping only works when you have already good material and you are only using that as a last step to close a few last pores. If you have not optimized parameters, or if you have some ugly defect, it's not going to fix that necessarily. And it can definitely reduce the properties in that case. But this, I would say this is in 0.1% of cases that happens.
Yeah, okay, thank you.
Thank you for the question.
Of course, we would like to have more of this discussion going on, but since the time is limited, if there are more questions and people interested in this topic, you can directly contact Anton.
Thank you very much,
Anton.
Thank you.
Thank you. We can move on to the second plenary lecture. It is presented by Dr. Klaus Pedersen from Dassault System. The topic of the talk is industrial design and process simulation for AM.
Yes, so hello everybody and good morning. So I hope you can hear me and everything's okay. So
yes, we have your voice.
Yep. So I want to present a little bit, take a little bit different take, maybe there was a little bit in the previous presentation, but a lot of the presentation I've seen so far very much focused on the experiments and finding material properties. So what I'm trying to show today is a little bit like where seen from my chair. So I'm working for Simulia at Systems, like where we are from a software point of view and what we are doing today. And this is something like from an R&D point of view, we now have, I guess, more than 5 years. We have spent quite a lot of resources on putting this together. So what I'm going to show today is a little bit like about generative design. We have seen a few presentations where there also have been on topology, and I think there's also some coming here after this talk in the morning talks. And then on the process simulation. But also I think like this one is actually very much under control today, or what should we say, partly under control today. So I think like more where we have a lot of emphasis is also to predict how things are in services. So we have seen a lot of great things also on fatigue prediction here with experiments, but I tried maybe here to put a little bit in more where how we can use our software to predict this. What is also a little bit important for a takeaway, I think a lot of these tools have maybe insisted for some years now, and some of you notice it, but what we have spent quite a lot of resources on is actually to integrate this one. So like I'm coming down for simulation, Simulia, so that's all over the place, but also to integrate the CAD world in it and also the Delmia work. So often for actually make this one productive, like in aerospace and automotive, is often that the engineering cost is a very big cost. So actually making a digital thread between the different processes. So I'm going to start with just showing some example of from generative design and then go down to the end and focus a little bit more on the end items here in my presentations. So here in generative design, I have taken a little bit different take also here to start with, because often what we see in the present presentations also previously is like we are focusing like that we can get better strength, we can get better stiffness, we can get lower mass. So this is like what is driving us. But if you go to company actually have to pay for it, then they will say, okay, what is my development time? If you have all these tools, you also have to be able to cut down the development time. So that's for like from the old days, if you have a time frame here and you're building something, you find out something doesn't work, you go back to fix it, then fixing becomes very costly because you're far down in the timeline in the design process. So for some with analyzing, we can go to this light blue curve and we can then push it down a little bit. But now introducing optimization, there actually the idea for often is to actually be able to reduce the development time and come up with the right design from the beginning, where to put the holes, where to put the membranes, lattices, or whatever you have in your additive manufactured design. So that's a driver. And also, I think what's a little bit different, what I also try to show today is like when we're designing, it's not just getting one design out, it's actually understanding like the constraints you're impacting the design with, what kind of variety of designs it will give you. So here I have taken a benchmark from 2019, because often it's very difficult to show from industry what people are working on, because the customers, of course, keeping the latest design very close. So here I have a benchmark which was run by the Zendia Lab as in the topology optimization round table in 2019, where we participated, and there was other academia and software houses also joining, and we then came in at actually winning this one. But let me try to show you what we did here. So we had here a suspension here from a Formula One car. And what you do in topology optimization is that we go in and fix, have a very simple, what we call a design domain, like where we want to put our design in for additive manufacturing. And then we have some boundary conditions, like where we're interfacing with the neighbor components. So we fix this one with other different kind of constraints. I'm going to talk about that from the modeling point a little bit later on also. And then in this case here, we applied 9 different load cases. And the overall target is to minimize the mass. But when we apply these load cases with the interfaces, we have to ensure a certain stiffness in the process. So here we have like a 0.12 millimeters on different locations here in the displacement, which it has to fulfill to get a certain rigidity in your component. And then you see here I also have 9 stress constraints. So each load case also applied to a stress constraint when we're minimizing the mass. But since I want actually to show that I want to compare different designs, I want to compare design obtained by additive manufacturing process, a milling design and a casting design, then I put an X here, because when I choose a different manufacturing process, I'm also getting different material properties in. So then we can now run the optimization. But as I previously said here, like in this one down the left corner, is that we have different manufacturing processes, and these ones we are then enforcing in a geometrical setting. It's not a physical setting, but they're enforced in a geometrical setting here. And for example, casting. So then you, for example, this one here, that left top here, you then have it casted, and then you see that you get these ribs here. The same thing we have for overhang. So if you have a certain overhang where you need a lot of support structures, we can go in and define this one. So for example, if you look at these 4 designs I have here, these ones I have minimized the mass for, and they have a displacement constraint, meaning that all the 4 designs, they have the same stiffness. They all have the same stiffness. But the design A, there's no overhang constraint in, so you probably need a lot of support structure when you want to print it. Design B is printed from the top, from the bottom to the top. The C is from left to right, and the D is from right to left. And then you see, like, if you go in and look here, you can look at then, of course, you get different masses out from the optimal design. And then you'll probably choose number C, because then you don't have any, or at least less post-manufacturing cost from that point of view. So that's the same thing what we, oops, so now my mouse is here freaked out. So let me just go here. So here, what we have here is then we have the additive manufacturing at the top. We have the mill design, and we have the cast design using this previous manufacturing constraints I showed for this one. And here the target is to minimize the mass. As you go nicely down, like in some iterations here, like 70, between 40 and 70 iterations. We have here the constraints. So here there's different, they're normalized because I have different stress constraints depending on which material I'm using for the certain manufacturing process. So I have here stiffness requirement for the displacement constraints. I have strength requirement for the stress constraints, and you see they're all fulfilled and feasible. So then now this is like something we have to be able to done for quite a lot of time. But now the thing is, like, you want to do a fast verification, because these topology optimization designs are basically living in a finite element world or CAE world. And then very fast in one click, we get directly direct modeling structure out, as you see here. And then the nice thing is, since everything is in this digital thread on our platform, then in one click, I just re-import all the 9 load cases, automatically remeasure it, and then right away I can start evaluating if my strength requirements for the additive manufacturing is fulfilled, the stiffnesses, etc. So this is this thing about, and I can also discuss with the people, like, what's the difference between if in aerospace we mill it compared with additive manufacturing, what will maybe be the downstream also cost for production. So these decisions can be done very early on. Secondly, this is still a lot of CAD surfaces. So people, it's actually a true CATIA model, but for example, for aerospace, but the question is, like, we still want to clean it up additionally. So then we have, of course, that we have the interfaces, like you see here for the clamping to the neighbor components. We have some surfaces hitting the outer surface, like of the design domain. And then so these ones we can automatically make one surface out of. But then we have a tool now where we can, like, for example, use a tubular modeler. So directly on the topology optimization from this direct modeling, we can then clean it up by just go in and sketch directly on it. And then we get reduced CAD parameters, and then we can then reduce it, and then we can manually modify where we want to have changes. So this is the tubular modeler, and of course we also have this traditionally just a direct modeler on here. So then in this process here, like a trained CAD guy will maybe take half an hour to reconstruct that design and do the detailed validation of it. So that means you get a design you can then use also later on in your aerospace workflow, etc., where you actually have all the CAD details on it, and not a data STL file, but actually something you can go in and modify in. And then, of course, milling is even simpler, because for this design we just have cut the 3 planes. So we have an automatic tool, and we get directly out a full parametric mill design from the. So in the optimization process, we had the mill constraint in, and also in the CAD model we have it in, and then we can then go in and do the full comparison of the final CAD model. We can put in, for example, into our Formula 1 car here, and then we can look at the masses between them. We can see the displacement constraint here is validated, and we see that the stress are fundamentally very, very different, because I have very different elastic properties, Poisson's ratios, and also the yield stress, because I have different material in the different designs I'm looking at here. So this is you can then use and then communicate to your colleagues, like, okay, what is the advantage of using additive manufacturing compared with some of the traditional design here, and then bring it out to that design. And then what I said previously is that a lot of these tools maybe have existed for some time, but are not really been integrated in a process where you just, when you have the CAD model done, you just in one click, you get everything remeasured, you get your connections and everything's in one go. And then that space is showing now setting up the model, a few hours, optimization, set up 15 minutes, running the optimization. Of course, in that time, you can do something else between 2 hours to a little bit more than 3 hours. And then the detailed CAD validation. here. So basically you can do that job here in one day for these designs here. And this is what makes this workflow very attractive to actually be able to use this kind of tools in industry. So what I basically show now is a full Azure workflow, basically where from the top we go from some loading on a very simple domain. We do our topology optimization, we can do the validation run. And again, designing is not just getting one design out, actually understanding what kind of manufacturing process, etc. I am imposing on the designer, how this impacting the design. But I'm just going to, this is my world, basically here in the optimization world. I want to go in and see some of the challenges we have resolved in that kind of work. So what basically happened there in the actual topology optimization is that we run our Abacus solver, we run what is called adjoint sensitivities, and we run a mathematical programming in our Tosca product. So basically everything is bundled up here in one go. And we can also include the, for example, like if you have contact is super important, but also constitutive nonlinear models if you have rubber in or other things interfacing it. So what's really interesting here is like, this is a very small model. I was considered today maybe with 500,000 elements in, but today we maybe make a model up to 50 million elements when we're designing a lot of details. And the thing is about this is basically living off what's called these adjoint sensitivities. So think about this being a Taylor expanse, that you're standing in one point and then you move down to minimum here, for example, for stresses. I know there's also been reviewing for a lot of optimization journals, and there's a lot of about machine learning, but machine learning is utterly failing for these kind of problems because we simply have so many design variables. So these adjoint methods are so fast compared with the analyzing. It just take a few percentage of the full time. So it's really a powerful way to design this ones. And I don't deep down this adjoint here on this slide, but this is basically the fundamental of it. Like basically do a small Taylor expansion of your design. And also an element being removed here in the process can also be reintroduced again if that's desired for the optimization problem. So it's not just removing element, it can also be reinserting them again. So then I mentioned a little bit like then the challenges that I just showed this Formula One suspension, one single component optimization, but in reality, the component is, of course, living in an environment interaction with other components, which can now becomes very super important to have this interaction between the different components. So here, for example, like a full suspension system being fully assembled here, where we have different components between them, and then we're also including all the nonlinear bushings in. Another thing is, for example, like in powertrain system, where we also do optimization for, is like that you actually have the gasket, you have a lot of contact, but even here in this case, the bolt are sampled so hard that you actually go into yielding. So when you're done with the bolt, you actually throw it out again and put a new one in when you're repairing it, for example. So here I take the example for aerospace, which is a door stop. So maybe it's a little bit difficult to see, but there's a little bit great background. And what we're doing here is that we take the 4 bolts here, so we can not see the 2 ones in the background that easily, but it's indicated here. And then you bolt these ones to the door. And this means that first you're actually introducing quite a lot of stresses in your component just in the assembling process, because you're bolting extremely hard, often over to the yield stress, not maybe in aerospace, but for other components, it could be like in automotive. And then afterwards, we have the 8 load cases here attached at the top of the head, which is kind of simulating when the door is open and closed in different positions. And this objective here, or this optimization, we have quite a lot of requirements, but I think today maybe not that unusual anymore. So the objective here is to come up with a stiff design, but we also have strength requirements so it doesn't break. We have mass constraints requirements. We have some displacement requirements. We have some force requirements on the bolts so they don't break and give a uniform pull in the door frame. And then there are some symmetry constraints, some member side constraints of how thin the structures parts can be. But in this one here, for example, then you will say, okay, I want to do some trade-off study between different materials, for example. So let's say here that in this case here, I'm optimizing this component. And what you see here at the top is one design. So it's shown a little bit from the angle, and here fully from the side. Here in the middle, you see one design, which is a little bit shown from the angle and from the side. At the top, we have 3 different designs here. So what the difference is between these 3 designs is that, for example, let's say I have a material with a yield stress of 900. Then the top design has a safety factor of 2, whereas the one at the bottom, where I use a stress constraint of 300, have a safety factor of 3. So when we go downwards here, we get more strength, and we get designs and which have a less chance for failure. But my objective was increasing the stiffness. So this is actually an example where I show that stiffness and strength are working opposites. So I often hear that as in optimization the people say they're minimizing compliance, they get good strength, but often we see that this actually working opposite. As an optimized strength, this stiffness design might not have the best strength properties, and this is exactly what this industrial example here shows. And what you see here is, of course, that when we have remember this one is clamped to the door, including contact. So when we apply the loads, it can open and close in the contact into the door frame. So we see, for example, this bottom design, they have a lot of arms here going into the door frame. So it has very different contact properties compared with the top design here at the top. Where it's just maybe has got the contact here. So again, very different mechanical behavior actually also when they're sitting on the door due to the assembly process. So what we are doing here in the assembly process, and I just want to show you, I don't go into all the details, there's a lot of papers about it, but in the literature it's not that often described. What I want to say, there's a few papers, a lot of papers on joint sensitivity, but not many describing this problem here. And when you have a bolt or you have an assembly process, you kind of preload it, and then you fix the bolt, and then afterwards you actually put it into the live load or service load. And that's what we're doing in the Abacus solver. This is standard. There's also connector elements for it, etc. But often the sensitivities are wrong because you have to add a lot of additional term because there is a time history in things. And this is what we implement actually to be able to predict, to include that preloading, because these components, when we're optimizing them, they're not just sitting in their own world, they're part of a world they're sitting in. And this we include here, and this so also in SMP and DMP, so distributed memory and multiprocessor, we can run very big models with it. So for example, just on this simple door step, what does this mean if I just use the standard literature for the joint sensitivity? Then I will get this bottom design here where you see there's a wrong design with holes in here, there's a wrong feeds, but you also see that from the optimization point of view that it actually give the wrong design. It has 9% too little lag in stiffness. It's converging very slow for some here on the strength requirements. At the end, the stresses are still fulfilled, but it takes much more time for conversion. Here, after 5 iterations, we more or less fulfill the strength requirements. Where we're not adding these terms, it doesn't. So this assembly process and everything is something we're looking a lot into. And then of the next step, what some customers now starting to doing is that also not just having the interface at fixed. One thing is you include the assembly, the bushing stiffness here for highly nonlinear rubber, and the preloading you include, but you also start including like, what if I change the interface a little bit, then my entire topology is also changing because I have a different force flow in the structure. So that's what you see here. So for different position, and Volvo did a very, it's also the thesis online, a very, also in a NAFEM conference paper, did a very comprehensive study of this suspension system in the back of the car and came up with a lot of different design, different position, and they also include the bushing stiffness, which is very important to have the right interaction between the components in the optimization process. So this is what I want to show, that where we are today, and I think optimization is not just getting one design, but actually understanding how you're impacting your constraints on the design and how this is influenced the optimization. So now I assume I have my digital thread for designing, that everything's okay. So I'm all set. I went from a CAD model to CAD model in my design process. And then I want to now do the additive manufacturing. So now I changed to process simulation. So that's kind of my second part of the talk, where I want to show what we are doing today or what we can do with our tools in Abacus here, integrated with the Delamere tools. So I take my, for example, a given printer. It can also be another printer. And here, then I put my component in, I optimized, I put in my support structure. So remember, everything here is a CAD model. So if I want to go in and modify something either in the red existing design, I want to test the small details, I can always go back and verify it. Everything's CAD and also the support structure. Then we read the laser pattern in from the machine setup, from the controller. We get the details in here. And then what we're now doing is that we are running a terminal mechanical analyzing. So we actually following the laser pattern here, and then we can do a temperature prediction as we go on. And then we can then do the modeling. So we find the stresses doing the printing. We can find the distortions here. And as you see here, it's a very thin support structure. So what's also turned out to be very important for this model, but we see more and more customers that you're printing doors and everything, thin structures in automotive, for example, we're really tight. Then buckling also becomes a problem. So buckling, to predict buckling, we can do that because in Abacus, of course, we can do geometrically nonlinear features. So if something is buckling, we can also predict that, but we can see for example in a thin support structure. So a little bit like what we did and how this is done, how a little bit of the background, how we are doing this, and what is our assumptions is that we assume that we have the machine and we have the the components on the base plate. And then we have, like in our tools, we have what is called the pattern eigenstrains approach. Some people call it the inherent eigenstrain approach. I'm not going to talk at all about this one because we very early on found that this didn't want to do downstream what we want to do. We can still implement it, but we often find it's actually failing for accuracy in what we want to do. So today I'm just focusing on this thermal mechanical modeling up here because it gives a lot of also downstream advances compared with the other approaches. So what we did early on is that we didn't want to have one process where you should print a lot of envelope, and each time you change something, you have to print a lot of new things. So what we did is that we want to have an approach which is not only for powder bed or the direct energy deposition or also a bit wire deposition. We want to have be like kind of a genetic approach. And we want, for example, like saying here we have a highly unstructured mesh here, you see in green here in this figure. So we want to very accurately to be able to model the surface. We don't want to be limited to a voxel mesh or something. So we want here to very accurately follow the surface, and we want to be able to follow the laser scan here. So how we did that without having a very detailed and blown up final element model and following the laser scan, we came up with an idea of homogenizing it. So you see this structure here is actually unstructuredly meshed, but you see the surface is flat. And the way the surface is flat here is because, of course, we deactivate and activate elements, but we can also cut through the elements. This is what you see here down at the bottom or at the top here. We have this little bit blue color. So we're adding up materials as we go on in the element. So what we're doing is that we're using a homogenization approach. So for example, if I'm filling in some material here, when I go up, this is a free surface, then I'm filling in also more conduction and convection here in the free surface and the radiation. So for example, in the thermal analyzing, I'm actually following also the surface. If that's a free surface, if that's an isolated surface, some powder where I have different properties. So we do that, and we also then include the melt pool sizes in the laser scan. So this is our approach to actually how to simulate this. So this means that we can still fairly coarsely mesh, like say using 500,000 elements for this model, and then we can still do the detailed layer by layer approach. And there are some, I'm not going to detail, like we know where we can skip things and where we can go a little bit faster, but this is kind of our approach. And this is also put into our Abacus solver. So then that's allowed us to use scalability. We can run on big clusters and everything. But today, like these models here, you can basically run on normal small workstations. It's not anything super critical from that point of view. And this is what the next one show, basically, that we can, there's also like from the scale point of view, there's not, what should we say, there's not anything limited from going from small scales to big scale with that approach as well. And I'm not going to, I think there've been a lot of great presentation about measuring and everything. So we have, like, of course, a lot of our customers are using these tools, so which cannot show the data, but there's been some like challenges here. You can also find more of these benchmarks where we do between our software and this. So the idea is again to do this more, what we call them blind prediction. So just using the constitutive material modeling. For example, if you look at the same red component here on the left on the base plate, I don't know, yeah, here you see these three ones on the base plate. And then the idea is then, of course, to have different temperature history. And then when we're comparing our measurements with our prediction here for the strains here, then we can then see we get very good correlation. Again, I'm not focusing a lot of all these benchmarks because they've been done a lot the last 2-3 years. On our homepage at the bottom here, you can find a lot of these stories here. I want to more to tell about what we can do downstream with this. And also another thing, often we get the question if I don't have my if I don't know which machine I'm going to print it on, but I want to just still test my structure, then we also have a very simple setup where we can, for the laser scans, we can use this pattern-based approach. So you can go in a user and just make your own pattern. You can also, of course, have your own controller you can put in if you want to, but here we just very easily allow people, and then to come up with a pattern, you can go in and define it, and then you give you a certain laser or machine properties you want to have that, and then we compare that with actually a machine you have, and then you can see the difference between these two. So you just go in and define these patterns, how you want to have set these ones up for your laser. So and then when we have set these patterns up, we then go in and take a component. So here, on purpose, I took a little bit of a thin wall components, what we see more and more of that people are printing. So here you see on the right-hand side, you see the laser pattern directly from the machine. And then we want to compare that one with our pattern approach compared with this one from the machine. And again, here I just put one component on the base plate. So they see the base plate is just a mesh with a hexa mesh. If you look in the zoom, you see the support structure is very thin. and they are modeled using shell elements. The duct here itself is modeled using tetra elements. So you see here that you have very different element types. And also if you want to put a lot of component on base plate, it's very easy today, even though the meshes are not conform. It's not like any nodes are hanging in the air, because we have these tie constraints where we can tie very accurately non-matching node elements together. So that's what we do. The shell elements, the tetra elements, the hex elements, we can then we can put a lot of components on, and this gives very, very good results both for thermal modeling and from structural modeling. So this is a very key feature. We can do that very fast and get very good results for that. And here again, our motivation, as I kind of try to stress, of course, we still need measurements, a lot of great work I've seen here, but our approach is to get down to the constitutive modeling, either whatever you measure them yourself or get them from a supplier. So here, for example, we have the conductivity as a function of temperature. We have the specific heat capacity as a function of temperature. And here with the Young's models, Poisson's ratio is not a function of temperature in this training workshop here, but if you have the data, you can also apply this one as a function of being temperature dependent. And we also, of course, have all our user subroutines also here, which you can plug in if you want to do much more advanced stuff. So here I'm comparing then using the pattern-based, which is the blue one you see here for 7 different points, which is measured here on the virtual printing. And then with the thermal mechanical one, where we actually took the one from the physical printer itself. And then we see like here that the temperature is at a given point here is, for example, 4% difference here at where we have the biggest difference between the 2 approaches. And also when we look at distortions, here we see that the pattern base gives around 2 millimeters, and around here is like 2.1 millimeters. So the 7% difference between the two approaches here. So this one seems to be very little bit design insensitive to actually how we're doing that laser pattern. So here, these methods have been shown very strong. It's just one example out of many we have done, and the customers have done, that these both using the laser pattern very actually give very good results, and also using this pattern-based approach. But again, for these ones here, I don't even include this one. We also tried to use the eigenstrain, the Harris strain approach, and they did not yield any accurate results also compared with the 2 other methods here. So what I think today in this virtual printing is, I think today we actually have the distortions very much under control. We have the stresses under control to be able to predict them. But now it's more actually coming more about like we want to go downstream and to be able to predict the microstructure prediction, the heat treatment, and in service load. So here we have put a lot of new keywords in and a lot of new options in since 2020. And I'm just going to show a little bit, just touch a little bit here in the last part of this talk about this. One thing is, for example, like here we're printing it with a benchmark we did with the Welding Institute in Cambridge. And here we see that we have the temperature, and then we have the next picture, we have the alpha phase transformation here in the microstructure. We have the beta and we have the alpha prime. So what we can then do here, we can then be able to predict the microstructures. So what happens is, like if I just go back to the temperature here, if I'm just choosing one point here and the laser is running around, then I have here, then of course it's melting here, and then it's go down again, and then suddenly the laser is in the neighborhood again here close to my point, and I heat up again, and then I go like this, and then I heat up again. So if we go to the phase diagram, basically I'm cooling down, then slowly I get heating up, and then I have a jump here, and then, so this, as you see in the left corner, is just one of many different models we have now put into our, also with respect to grain sizes, etc. We have put into the allowing to use that as standard tool for the microstructure prediction. And this of course also becomes very, I think where we see a lot of requests is in heavy machineries, like where people maybe make a component 5-10 years ago and then it wear down, and then they try to, instead of making a completely new component, then they try to repair it using additive manufacturing. But then of course what happens is that you're also reheating some of the existing material, and then you'll also be able to change the material properties for that one because you're reheating it. So this is what we see more and more for actually using additive manufacturing for repairing, in particular like in shipbuilding, in oil industry, or in other heavy machinery industry. But then they want to predict like how the actually temperatures influence the entire component when they're starting repairing it using additive manufacturing. very short slide here. I was like, I've seen a lot of nice presentations also here doing that. There's also a lot of things on plastic going on. And for example, here we can be able to predict the volume fraction. This is a very old design from 2017, so I can show this one here from the university. And then you see that the volume fraction of crystallization in the process here going on in here. So this is from 0 to 0.84 here. So this is also things we can predict. And again, in our homepage I had before, there's a lot of details about some of these benchmark and how this is set up. So I think now is that now we are now in the state where we can start to actually be able to do the heat treatment and also predict the residual stress after some heat treatment, also how the microstructure is. Also is that the machinery, when you cut it off the base plate is one thing, but also see when you're cutting out a red hole here, if you not have any stress release heat treatment, then of course you'll do some stress release in the cutting process, and this we can also predict. So now I'm just going to the last example here. I hope I have time for that here. Is this be able to talk about a little bit about how we can use the residual stresses we have here for be able to maybe predict something about fatigue. And again, I think at this conference there's been a lot of interesting talks about fatigue and how to actually find SN curves if possible at all, and this is what I try to use some of these data in here to be coupled with the manufacturing process. I see there's a presentation also here, I think around 11 in here. I just saw the video from NLR where they're also trying to do something similar like this one here. So I'm also looking forward to discuss that presentation. So here the idea is that we have a normally fatigue. So we go into take our Abacus results, and we have a tool called FESAFE where we do our fatigue calculation. So we have some channels where we have some loading in. So we have some time histories for the loading, and then normally you're using linear superposition of these time histories you have, and then you can calculate the fatigue factor based on going to SN curve. So here, just the one designer show here is just assuming no additive manufacturing, isotropic material, uniform, and then I can see that for this design here I have a reserve factor around 5, so I can still load it up by a factor of 5 before I actually get fatigue issues. So then I want to now compare it with what would happen if I made this component here using additive manufacturing, and I put it on my base plate. So I'll go a little bit fast because I don't have so much time here. And then I take some, I get the different properties here depending on how it's located, etc. And then I have my SN curve. So this is where I see a lot of great work being done. So I take my SN curve from the experiment, and I have my stresses down for the printing. And then I see that actually when I do that, include these properties for my printing, then I get a reserve factor of 3.2. But in reality, as we just discussed, then of course you have here that you want to include the residual stresses. So on the other one, I just include the SN curve, but I didn't include the residual stresses. So then next step is to include the residual stresses. So we see we have the terminal run, we get the mechanical printing, we have the residual stresses. Then it comes out, we cut it off the base plate, we get some stress releasing, but also around you see like where I have these squared holes here. And when I'm cutting these ones out, I also get some stress release around that point also. And then I take the residual stresses, I plug them in, so my mean stresses, etc., and everything is increasing when I plug this into my fatigue calculation, and then I get reserve factor around 1.5. So it has a big impact, of course, depending also of what kind of heat treatment, etc., you're doing. But it has it's become very unsymmetric. There's no fatigue issues on this side. Everything is sitting on the left side here. Then what we also talk actually pretty interesting in the previous discussion is like what happened if we print very fast inside, so we get some flaws inside, so we get some weaker material properties inside. Actually, this is what we tried here. Maybe that's because we didn't do that in our printing process close enough to the surface here. So just inside we went a little bit faster, we get weaker material properties. And we saw that this actually didn't inflect the reserve factor at all. Of course, when we get closer to this critical area, then of course we will see more of that effect. So then the next one is that I just told in beginning that I did a big mistake, because in reality you're not just going to print one component, you're going to print a full set of components. So when I'm now printing quite a lot at the same time, you see that the heat distribution time or the time history is very different. Some are very close to the base plate's free surface here. Some are maybe more isolated from a temperature point inside here. You see the temperature field is very ununiform. That actually means that when we went in and look at the stress distribution or residual stress distribution, this component, you have a fluctuation of this case here, at least for minus 15 plus minus here. So then we took the worst case and the highest with the highest stresses and the one with the less stresses. And then we see that now we get a reserve factor in the last case here, not just one value, but actually understand that I'm printing the same component in a lot of different position on it, would have a very different temp history also, because depending on your laser pattern, what kind of laser pattern you're using, or if you're using multiple lasers, then we see that we get a difference here in this in the reserve factor of 1.8 to 1.3. So the answer is again not just one answer, it's actually a distribution of answers of this here. So sorry, went a little bit fast here at the end. So I think what I've tried to cover is quite a lot of things. So I tried to show that the digital thread that we're aiming on from generative design, always keeping things in a CAD model, we can modify downstream in the process. So we went from optimization, from CAD to CAE optimization. Optimization is not just getting one design, but it's getting a group of design, understanding how the constraints you are having for your design, making a library of solution. Then I focused on the downstream process afterwards on this one, a digital thread of actually doing the process planning, where we have different tools now also put in with the patterns. And then I think we are very far today. If you have your constitutive models for your conduction, your Young modules, Poisson's ratio, function of temperature, you have your convection, conduction, you have your laser properties, or for the laser machine, you have your controller settings. Then I think we actually today we're very mature and be able to predict distortion and residual stresses. And now the focus is actually a lot of downstream, like microstructure prediction, heat treatment prediction in services. So I think this one here, actually the last 3 years, 2-3 years, is actually very mature these days. And now the issue is actually more to look at the very end, for example, fatigue and how things are doing in services. So of course, there's still a lot of opening, and you can do a lot of deep dive on a lot of the topics here. But I just very fast try to give an overview that where I think that we are standing from an industrial point today, seen from my chair here at Dassault Systems. So thank you.
Thank you very much, Dr. Pedersen, for this interesting presentation. It was quite nice and useful to know that the numerical modeling, we can go so deep into the details of production, either AM or non-AM techniques. From the audience, if there is any question, yes, we have one question in the chat. Harry Sihoyos has asked, could you please briefly explain how the laser heat source is implemented on the thermal simulation of whole part?
So let me try to go to the slide here. Yeah. So what we will have to do is that we go in and define the melt pool here, and how fast this is and how the sizes is that. And then it has a certain radius here, and then yeah, you can hardly see the equations, but there are some equations down here for how the sizes is of this melt pool and how this melt pool is defined. And this is of course where we don't do any details of including the gases or anything like here. We just assume we have a given melt pool here in this one. And I didn't include this one, but we also have examples where we are kind of showing like where it's the melt pool is influencing like a neighbor material, like it's somehow half get through where it had been before. So this is this, and we can also do like if you have a string laser or different setup where you're printing in a different way, for example, plastic, then yeah, so that's so we don't do what should we say, like any detailed CFD or anything like that here. We just assume that we have a certain a melt pool, and then you can describe the properties of that melt pool. Yeah.
Okay. Thank you. There is another question from the same person. He has asked, can melt pool characteristics or defects of the part be predicted within the software?
Yeah, I mean, to some extent, like there's some empirical things would have to go in there, but we have some results, like for example, like for this one here, let me just show this one from the Welding Institute here. That one, for example, that was pretty funny because first we got some results we couldn't believe. This is pretty old results by now. We got a results we couldn't believe, and then we said for example there was we saw there was in our first run we saw there was unutilized powder and everything. So it's kind of weird, this laser scan, and then when they actually printed themselves, they saw some of the same defects. So for example, we don't get any surface quality anything out like this, but we can to what we saw in the previous presentation, we don't get anything out. One could say for example in the previous SN curves, of course, when I'm showed before, these ones would have been improved there, included there in these curves, of course. But here, for example, we can see if we have unutilized powder, etc. In here, that one we actually by mistake, this very old design here from 2017. So that actually was pretty funny. You see, like this one, yeah. So somewhere we'll have like this little bit maybe in the right corner. You can see that we have these dots here, where we have the alpha prime here, and that defects we actually they actually measured on the also on the experiments when they were doing this here. Yeah.
Okay. Thank you. Any more questions from the audience? I actually have one small question.
Sure.
So as a tool, this numerical model, we can use it possibly to set the process parameters to get lower level of residual stress in the component.
Yes.
By having a model. So is there any other way than manually changing the process parameters and see their effect on the residual stress? Is there any intelligent iteration that the software can do it by itself and give us the proper process parameters?
Yeah, we have our own presentation where we use a simple DOE method to actually tune if you want a certain target, like there's also time and speed and etc. So we have a presentation which, if somebody's interested, you can reach out. I don't know sure if that one is on our homepage, but we have a presentation from Manafran's presentation where we're using this one to actually calibrate what is the optimal parameters to use for a given setting or what you want to achieve. And so that's cost and speed, and at the same time you want to have a certain level of residual stresses, for example, a distortion, or you don't allow a certain as a constraint. Yeah, maybe I'm saying too much now, but we have actually a few machine manufacturers using our software to tune the controllers, so they can start with some processes also before they actually build the machines.
Okay. Okay.
There have been to some of our user conferences. There have been a few manufacturers actually showing some few presentations, but normally they don't show too much. Yeah.
Thank you. Since there is no more question, I would like to thank you again for your presentation. And if there is interest in this presentation, or if you have any questions, you can directly contact Dr. Pedersen.
Yes, feel free to reach out. Yeah.
Thank you.
Yeah.
And thanks to the audience of this session. I hope you enjoyed the rest of the conference today, and wish you a nice day. Goodbye for now.
Okay, good morning everyone. I'm Davide Paolino from Politecnico di Torino, Italy. I'm glad to chair this 7th session entitled Computational Process and Property Prediction and Topology Optimization. The first talk, I think that we can start at 10:40 according to the schedule. The first talk is given by Professor Sindinger. Hope
yes.
the pronunciation
but I'm not
is
a
right.
professor.
Okay, and from Linz University. Please present your short presentation about the activity.
Right. Just thank you, Professor Paolino, for the short introduction. I hope you can see the slide and hear me. If that's the case,
yes,
I would like
to
hear. Present our topic, which is entitled Considering Inhomogeneous Material Properties for Stiffness and Failure Prediction in Thin-walled Additively Manufactured Parts. So additive manufacturing and in specific laser sintering enables us to produce complex lightweight components for production of functional prototypes or small series parts. Thereby, such components often feature thin-walled structural members as depicted here on the right, which can be in shape of some kind of ribs, for instance. Thereby, the thickness dependency and the superimposed anisotropy of the laser sintered material constitutes a major challenge for structural finite element simulations prior to part fabrication. Hence, it was the aim of this research to investigate an approach or a possible approach how to account for this thickness dependency and anisotropy in shell mesh simulations. The proposed methodology comprised the following steps. First of all, the material properties were characterized by quasi-static tensile testing, which is depicted here. Several build orientations were tested in various thicknesses. The next step involved a material modeling stage. Here, for instance, is the Young's modulus displayed, plotted over the part thickness for different build orientations, which depicts the thickness dependency, and also the orientation dependency or the anisotropy was modeled as well. This was done for both the elastic compliance metrics as well as for a failure criterion, which was then also considered as thickness dependent. The next step involved property mapping in the finite element models. Here just the general setup is shown, and below the color coding refers to the different material properties that were automatically assigned to each element. Ultimately, on the bottom you can see a contour plot of the thickness dependent failure criterion, which was derived of the orthotropic Hill criterion. The last step involved experimental validation of this kind of three-point bending setup, and it yielded the following conclusions. Overall, it was found that both the stiffness and the strength prediction or failure prediction could be improved significantly when the inhomogeneously mapped properties were used in comparison to the conventional homogeneous properties. While this led to satisfactory results in terms of stiffness prediction, in terms of failure, further still considerable deviations remained between the simulation and the experiment, which means that further research is necessary or required to improve failure prediction in thin-walled additively manufactured parts. Ultimately, this once more highlights the fact that the structural integrity or failure of structures is very much dependent on local phenomena, while the stiffness prediction of structures can be or is much more smeared out and can hence be predicted more easily. This was my short introduction to the topic or to the conference contribution, and please feel free to ask any questions you may have.
Thank you, Siegfried Lorin. Is there any question from the audience? Yes, there's a question. Please.
Yes,
Klaus?
Klaus here. So,
yes.
So I was just wondering also, when you're doing this, you have the FE property mapping. Is that one optimized also using the Hill criteria? So you try to actually optimize the structure using the Hill criteria in that one also as a constraint when you design it, or what? Or that's your aim,
No.
or what's no?
No, actually, in this step, just the part is designed, and then afterwards it is assessed using the structural analysis to investigate if it even makes sense, or if actually an improvement can be achieved in general. Obviously, in the next step, it would be the target to implement it directly in the design process or in the structural optimization.
Yeah.
But this was not yet conducted, because in every optimization iteration, when the thickness, for instance, changes, or the layout of the rib, also the property of each element has to be once more mapped. And we wanted to check in this simple case first before we come up with the framework that automatically maps again the properties between each iteration.
Okay. Okay. Yeah.
Yeah.
Thanks.
Thank you. Is there any other question from the audience? Okay. If no, I am some curiosities. Indeed, the first one, the geometry of the specimen used for the validation is quite complex. How did you define such kind of geometry for the validation?
Yeah, our industry partners at KTME Technologies,
okay,
they wanted to have like a structural part as shown on the right, or something like this right from the start, and we were like, we would like to investigate only on coupon level, and then we made a middle choice, so we made a little bit more complex part, but not as complex as a real lightweight component. So we came up with this relatively simple 3-point bending beam, and the layout of the ribs is derived of the principal stress trajectories, and yeah, that's
okay.
The principal stress trajectories for the given load case, and that's of course how the layout of the ribs was defined.
Thank you. I think that there's time for another question by Professor Torgersen.
I have a question, maybe I just didn't get it, but what is the role of this outer bounding box? Because obviously it doesn't relate to the stress lines, right? So is it just to connect the members, or is it does it have another role? Because I'm guessing especially the corner will have an effect on the properties.
Yes, it was to connect the ribs, and also the research is part of an ongoing project where different sandwich-like beams were investigated that had lattice cores inside, and the outer boundary was actually also taking or designed to be aligned with the previous research, which however is not shown here in the presentation.
Okay, thank you.
Thank you. I think that it's time to pass to the next presentation. Thank you again, Siegfried Lorin. Let's go on with the next presentation given by Giuseppe Macoretta from the University of Pisa. The short presentation is entitled Productivity-Oriented Process Parameters Effect of the Fatigue Strength of SLM Inconel 718. Please.
Yeah. Thanks. Can you hear me?
Yes.
Can you see my screen? Okay, perfect. Yeah, just a brief presentation of our work. This work is a preliminary assessment about the effect produced by different process parameters, productivity-oriented process parameters on the fatigue strength on Inconel 718. We know well the shortcoming of ESIAM technology. In premise, first of all, the lower productivity rate compared to traditional manufacturing process, part of the poor cyclic mechanical properties and so on. How can we speed up the process? We can install additional machines, we can introduce multi-laser machines, or we can try to speed up the process by specific process parameters. In particular, in an area of the component where it's possible to have a worse roughness, let's say, but let's say, as example, better production time, let's say. This is the third, this way is the way that involves less cost. And our work was to try to find develop productivity-oriented process parameters and test the fatigue effect that they have. How we define the process parameters, we used a simplified model that we developed, and we used process parameters that increase the aspect ratio of the mel pool, increasing the laser power and the scan velocity in order to be in the feasible region, but have process parameters that, if we consider a simplified job with the small square bars and 20 bars in the job plate, we can have a reduction in the job build time of about 45–50%. So we can halve the job build time compared to standard process parameters with the two process parameters A1 and A2 that we developed. We printed specimen class standard fatigue, plain fatigue specimens in vertical direction with our printing machine Rayson 500E. We tested in S-built condition. If we see the effects of process parameters on the microstructure, we see that the mel pool shape is almost similar, but we have an increase in porosity and in roughness near the surface. We can see this increase in porosity, in particular, seeing the pore aspect ratio that becomes more elongated, showing pore that are from lack of fusion more than gas entrapped porosity. And if we test also the surface roughness in terms of, we measure it both by profilometer and by section extracted in the specimen longitudinal direction. So standard metallographic section, we extracted the profile, we computed the profile. We see that both the two way of analysis show that increase the productivity-oriented process parameters produce an increase in their surface roughness, important increase, and that this technique based on extraction from metallographic specimen produce a more detail. We see that the roughness are monotonically bigger than the one measured by the profilometer, naming that, showing that we are able to see all the small notches that can produce fatigue crack. If we see the result in terms of fatigue strength, that surprisingly, we see that the reduction is very small. We have an important increase in pore dimension and more important increase in roughness, but the decrease in fatigue strength is very low. In particular, for A2 is only 7% in terms of fatigue strength at 1 million cycles. The cracks started all, in each case, on the surface. And another effect is that of the productivity-oriented process parameter, that we have additional cracks. We see here that we have the fracture surface, but very near we have another valley with another small crack that started to propagate and then was not so favorable as the one that produced the fatigue crack. So just to summarize, we introduced two process parameters that introduce an important increase in productivity rate, but even if they produce an important increase in the roughness, the reduction in fatigue strength is very small. Thanks. To be in the time.
Yes, thank you, Giuseppe, for the nice presentation. Is there any questions from the audience? Okay, I think I have just a couple. The first one is, do you believe that the build orientation can influence the fatigue strength comparison? Since, if I'm not wrong, you only run vertical specimens. So what do you believe about the effect of the building orientation about?
Yeah, for sure, because in our case, the increase in the process parameters, in the speed, the power, source, and the speed, is a roughness that is roughness related to the superposition of layers and to the stability of the lateral boundaries of the specimen. Because when we increase the size of the melt pool and the power that and so the energy density that we introduce, we have this roughness that is related to the stack of layers. In these parameters, we have used a standard layer thickness of 60 microns, so the vertical resolution is the same. Yeah, it's clear that in horizontal direction, we can have different effects. First of all, because of residual stresses that can be very different, as we well know. But also, in terms of roughness, we can have introduced effect of downskin and upskin, so on the two sides of the specimen, let's say, the sample. So the vertical direction was chosen in order to avoid downskin and upskin effects on the gauge length of the specimen. Yeah. But it can be very interesting to test also other directions. Yeah.
Okay, thank you. Other questions from the audience? Otherwise, I have just another one. You mentioned the A1 and A2 for a set of process parameters, but I don't understand if they have been defined in the presentation and what kind of parameters you used and how did you define them?
Yeah, it was too brief probably in that part. Yeah, these two process parameters are defined keeping constant the layer thickness compared to the standard process parameters used for Nikon R719 in standard process parameters provided by machine manufacturers. Let's say. We preserve the layer thickness, and we working on a feasible region that is based on a simplified model that will be presented in a paper that is under submission. We are working this day, and I cannot provide too much detail on that model, but it's a model based on the Rosenthal solution of a moving point. It's also a simplified model, but we analyze also the literature data and the data from our tests. We think that this model can predict reasonably the feasible region of the process. So the two process parameters are taken increasing the aspect ratio of the melt pool. That means increasing both laser power, scan velocity, and H distance in the same with different ratios, but in order to have the more or less the same, let's say, safety factor on the lack of fusion line. That is the green line that you can see on the graph on the right. So our idea is to exploit the feasible region of the process, continuing it also towards the part of high velocity, high power. That is a part that is not so explored by literature and by parameters provided by manufacturer, because you increase a bit porosity, you increase roughness. But our idea is that in that region, you have not so much lack of fusion and porosity, not so you have not the effect of so destructive lack of fusion that can decrease significantly the fatigue strength of the material, let's say.
Okay, thank you. Other question, just one quick question. Okay, otherwise we can go on. Thank you again, Giuseppe.
Thank you to the audience. Trying to understand how I can. Okay. Found the correct button.
Okay. The next presentation is given by Professor Hoch-Wallner from TU Vienna. The presentation is entitled Molecular Dynamics Simulation of the Mechanical Properties of Photopolymers Used in 3D Printing. Please.
Yeah, thank you for the introduction, but I'm also not a professor, also doctoral student at UWien, the Institute of Material Science and Technology. And we are dealing in our group with resin development for stereolithography. And this kind of material, the properties of this kind of material is strongly depending on the polymer network structure. So in the experimental approach, the material is well characterized in terms of mechanical properties, but we do not get direct information on the network structure, which is basically the defining property of these photopolymers. So that's the point with in silico simulations. So within the framework of molecular dynamics, we are trying to simulate the network structure and simulate the mechanical properties of photopolymers within, of course, the limitations of molecular dynamics, where we have to keep in mind that we don't get a digital copy of reality. We rather get, or we try to get a model that is within certain parameters, a reasonable approximation of reality. And we hope to learn something about the network properties relations, and for the future we want to try we want to have material screening before synthesis, or even further in the future automated resin discovery. So but let's keep it to the basics for now. Molecular dynamics, the chemical information is brought in via the parametrization of the molecules. This work, first of all atom representation was used, where each individual atom is modeled by one atom in the simulation. And secondly, coarse grain representation, where chemical groups are grouped together to form a so-called coarse grain bead. We then simulated the network formation of TechDMA. Here's a rendering of this simulation. Yeah, here we can study where the reactive regions are, and we try then later on to relate the local double bond conversion to material properties. But I will skip this video for now for time reasons. So what we can then do is evaluate reaction kinetics. Reaction kinetics, of course, is a critical value for 3D printing, for process speeds, of course, and also for the mechanical properties later on. So here, and at the top right graph, you can see the simulated polymerization of neat TechDMA. The x-axis is the attempts, and the y-axis is the double bond conversion. So the molecular dynamics, so the polymerization code tries to form a bond, and if this is successful, the double bond conversion, of course, increases. And we can see in TechDMA that we have a rather quick polymerization until it stops abruptly here, slightly above 40, at 40 to 50% double bond conversion. This is in contrast to the monofunctional methyl methacrylate, where we have also a rather quick polymerization in the beginning, flattening, where at higher double bond conversions. So polyethylene glycol, you can see here, which is compared to the others, is a very large molecule, and we see the expected behavior, not very reactive material. So what it is done in practice is that it is mixed with reactive diluents like the TechDMA or the methyl methacrylate, and you can see the reaction kinetics of the mixture here. So similar to the others, very quick in the beginning, and then also some flattening above 60% double bond conversion. What we can also do is small strain experiments. So we take the simulation box and this strain it periodically, and we can measure then the storage modulus. And you can see here a comparison with a real experiment, so with the real storage modulus measurement of a photopolymerized TechDMA. And we can see the data points over a range of temperatures, which has a nice similar to experiment relation with temperature, and also the double bond conversion relation is also rather, yeah, it's quite good. So the expected behavior is that storage modulus is decreasing with decreasing double bond conversion, which is represented by the simulation. We also did large strain experiments. So the simulation box was strained, and the stress was measured basically. Here the blue curve is the methyl metacrillate material with 90% double bond conversion, and you can see a nice yield point here at around 80 megapascal and 10% strain. And going down with double bond conversion, we can see that the yield point is flattening out, and with here the red curve represents 60% double bond conversion, where we don't see any yield point anymore. I can always speculate this is probably only a gel-like or viscous liquid-like material. And with this, I want to thank you for watching, and I'm open to answer any question.
Thank you, Alexander, for the interesting talk. I think that there's a question by Professor Torgersen, please.
Thank you very much for the very interesting talk. I was wondering what your inputs are. Do you have some certain, I'm guessing the photopolymerization has certain likelihood of happening, right? So you have also different types of polymerization going on. You have the cross-linking between the PEC DMA or PEC DA, what you had, and then you have the sort of reactive diluents that are growing like a chain. Is this all handled in a probabilistic regime? So do you have kind of a probabilistic scenario if either one or the other happens? And is there a scenario that links these together? Basically, can a reactive diluent react also to a cross-linker?
Yes, so for this work, the reactive groups were all the same. So it was assumed that the likelihood of each reaction is the same.
Okay.
And it was only a simple cutoff criterion applied. So if the reactive and the active particles are within a certain distance, the bond is formed, and otherwise no bond is formed. So, but there is no probabilistic method applied. It's only the cutoff criterion. But for future, so we also want to, so termination reactions are also, and recombination reactions, this was also not taken into account in this work, but will be taken into account in the future, of course.
Do you take in, does this model take in steric hindrance effects?
Yes, so the molecules all have a certain stiffness, of course, and this hinders the reactive groups from coming closer together, or it even keeps them together depending on what chemical groups you have. So this is all in the parametrization of the molecule. There is all the information.
All right, thank you very much.
Thank you. Other questions from the audience? Okay, just a very quick one from my side. Probably I missed something, but I do not understand what are the dimensions of the box that you simulated, and how much is the computational time for simulating?
Yeah, so the box is rather small. It contains only 500 molecules in the TEC-DMA example. Because, of course, of computational power that is needed. And for this large strain experiments, I think it took half an hour for one of these curves. So it's actually pretty quick for a molecular dynamic simulation.
Okay.
Yeah, so it's okay.
Okay, thank you.
You're welcome.
Again, Alexander, so we are perfectly in time, and we can pass to the next presentation, which is given by Tim Koenis from the Royal Netherlands Aerospace Center. The presentation is entitled Full Process Chain Simulation of the Wire-Based Laser Metal Deposition Process Towards Fatigue Life Prediction. Please, Tim, you can start.
Yes, thank you for the introduction. So together with my colleagues Wouter and Marco from GKN Aerospace, we have been working on the full process chain simulation of the wire-based laser metal deposition process towards the fatigue life prediction, which I will shortly present here. So as you have already seen in this conference many times, there are a lot of aspects in the metal ESIAM process that can influence the fatigue life. And this for aerospace parts, this is difficult for example, certification, as the fatigue life becomes a bit unpredictable. In our study, we studied the LMD process, which you can see here on the right, where for our case, a titanium alloy wire is fed into a laser beam, which then melts the wire and then deposits the molten material on a substrate plate. And then by depositing multiple tracks, you can build up your three-dimensional part. Similar to other ESIAM processes, this process also requires multiple post-processing steps before you can actually use your part. For example, heat treatments are often applied to either improve the microstructures or to also perform stress relief treatments. And also machining or wire EDM is used to obtain the correct dimensions of your part. And as you have also seen in this conference, both these post-processing processes can also significantly influence the fatigue life of your part. So with this problem, we stated the question if we could apply state-of-the-art virtual manufacturing to develop a virtual manufacturing process chain to see if we can predict the fatigue life after the complete process chain. And for now, the state-of-the-art is mainly focusing on the residual stresses. So we, for now, focus on the effect of process-induced residual stress on the fatigue life of these LMD processed parts. I will show our framework using this simple use case where you have a simple wall being deposited on a substrate plate. And then in this geometry, the bracket is already included. And then we track the residual stress throughout the complete virtual process chain. So after we start with the LMD model, which we developed, calibrated, and validated with experimental data. And after the LMD process, we obtained this residual stress profile where you can see relatively high residual stresses and also concentrated near the base plate. And then we performed a simple heat treatment simulation to perform a stress relief treatment. There you can see that the stress is homogenized throughout the part and also the stress concentrations are strongly reduced. And this is followed by the wire EDM simulation where we remove the excessive material to obtain our final part and also the final residual stress distribution. And then to go to the fatigue life predictions, Klaus also presented something similar this morning, where you have the SN curves of additive manufactured titanium material, and then combine this with in-service load of your part to obtain the fatigue life of the part. So if we do not include any residual stresses, you have a nice high fatigue life, where in the end it starts to fill at the connection points with the base plate. Then if we do include residual stresses of the complete process chain, you can see that due to the stress concentrations that are still remaining at these connection with the base plate, the fatigue life starts to reduce significantly. However, we can also use the same method to, for example, investigate effects of different process steps or process chains. So for example, when we do not perform a stress relief treatment, we can see that the fatigue life of the part is even significantly more lower. So this shows, for example, qualitatively that performing a stress relief treatment significantly improves your fatigue performance. So a short overview of the framework that I just discussed. We first perform a calibrated and validated LMD simulation to obtain the residual stresses throughout the part. Then perform a simple heat treatment simulation, which is not yet validated, which shows the homogenization and relaxation of the stresses. Then also the wire EDM simulation. However, this is also not yet validated and is for now only usable for small deformations. And then we also have the fatigue life predictions using SN curves, which now only gives qualitative estimations and, for example, can be expanded using porosity predictions or any other interesting effects. To conclude the work, so our virtual process chain framework for now gives qualitative estimation of, for example, effects of different process steps, and then can also be used to optimize these process steps to increase, for example, the fatigue life. However, some validation of the individual processes is still required, as only the LND process has been validated as of yet. So the outlook, we will first continue with the validation of the individual processes, then apply it together with our partner on an actual additive manufactured aerospace bracket. So thank you all for listening. And if there are any questions, let me know.
Okay, thank you, Tim, for the nice and interesting presentation about simulation. Is there any questions about this talk from the audience? Okay, one from Klaus Pedersen, please.
Yeah, thanks for the nice presentation here. On this one, with your times you had, how should one understand these times you have under these figures there exactly?
Oh yeah, sorry, that's the simulation time. So you can see, for example, for the wire LMD simulation, it's quite short because we used a quite low fidelity simulation method. So we simulated these track by track instead of actually having multiple time steps per deposition track.
Okay, so that means basically you can run the entire workflow on your laptop more or less. What you have here. I mean, it's
exactly.
Actually pretty fast turnaround. Even designer times you're down to here. So okay, interesting.
Yeah, we mainly use this low fidelity approach because then we can maybe in the future also use this to optimize the chain. So then you don't want simulation times of multiple days, but actually try to shorten the loop.
Okay, so the idea is to put like a DOE algorithm or something around it and then do some simple modification for the design, see what happens.
Yeah, exactly.
Okay, interesting. Yeah, thanks.
Thank you. Another question by Harry Psioios.
Good morning. I just want to ask if you will include porosity or defects in your model in later stages.
Yes, thank you for your question. For now, we have only implemented it in the SN curve. So we based the SN curve on measurement data that included some standard AM porosity. But you're also indeed looking into trying to predict the porosity in the part and then include this in the fatigue life prediction. Yes.
The SN curves are the specimens that you get the SN curves have been produced with the same process parameters as the part?
No, as of this time, not yet. We have received from our partner the materials that are produced in this similar method, and we are going to test them, but we don't have those SN curves yet. No.
Very fine.
Okay, thank you again, Tim. I think that we can pass to the next presentation. The next presentation is given by Marcus Lid from NTNU. The presentation is Marcus Lid present. Okay, the presentation is entitled Finish Pass Strategy to Improve Sidewall Angle and Processing Time in FIB Milled Structures. Please, Marcus.
Hello. Can you hear me and see my
Yes.
screen? And you can see my screen as well?
Yes.
Okay. Well, thank you for having me. I'll be presenting to you on this finish pass strategy to improve sidewall angle and processing time in fib mill structures. So just very quick, what is the focused ion beam or the fib? I know it's a bit different from what many of you are doing. Usually it's in such a dual beam setup with an electron beam and an ion column. And once the ion beam it has sufficient energy, yeah, it will look something like this. And the ion column, the ion beam will have sufficient energy to sputter away atoms from the target material, and this can be used to you can then scan the beam in a certain way to mill the structure. And it's a bit different from what many of you are doing, and it's not really an additive approach, although you can flow a precursor gas to actually build structures. But I hope this is going to be interesting for you anyway. Many people might be familiar with using the fib for doing material characterization and cross sections and such, but you can also make structures and patterns. And what many people will be doing is you're scanning over a certain pattern in what a process will be called bulk milling, where you have a certain scanning pattern which is repeated over and over and over again to reach a certain depth. This has a drawback that you'll have the sputtered material may redeposit on the sidewalls, giving not the final structure that you want. What we're trying to do in this work is coming up with an approach where we're applying a finish pass, where we're scanning the beam multiple times along the sidewall, seen with this diagram that this final pass, we're removing sections gradually towards the final sidewall angle. And we're able to do this using pattern scripting to create the patterning file, which we can then send to the ion beam instrument. And this is done with a Fibomat package. So to test this, we made 3 different test samples. You can see this test geometry over here. This is on the micron scale, so it's quite small. And the whole pattern is a few microns in size. And the first one is just the bulk milling. The second one has 1 finish pass using the same beam currents. And then in the last sample, we're having 2 different finish passes, but we're also using different beam currents. So the beam currents are going to be related to directly related to the milling time. So a higher beam current will be a much quicker milling. And then in the final finish pass, we're having a smaller beam current. And the smaller beam current is making the beam size much smaller. And by that, we're able to have a much finer control and higher precision. This is results. Here you can see in the 3 different columns, the 3 different samples, the bulk milling and the bulk with 1 finish pass, and bulk milling with 2 finish passes. As you can see from these details along on the top view, there's these corners are becoming much sharper and more distinct with the finish passes. And we have these grooves, these channels, which I deposited with platinum. We filled them with platinum and then made cross sections to see and to better see the sidewalls. And here we can also clearly see that the sidewalls have a much are much steeper. And and so we measured these angles, and there's clearly a much steeper angle. And then it's interesting, this aspect of the milling time. So as one would suspect, or is that the milling time would be the same for the two first samples because we use the same beam current. So we applied just the same amount of dose on both of those samples. But on the third site, we had a higher beam current for the bulk milling, which results in a much quicker milling time. And then we can use the higher beam current, the lower beam current for the finishing details, which makes it, in this case, somewhat shorter processing time. And probably we could have also cut out this last step and also gotten an improved quality with a much lower milling time. So I think with that, I will stop presenting, and I'll be happy to have any questions.
Thank you, Marcos, for the interesting talk. I don't know if Klaus Pedersen has raised his hands for making a question or not. Okay. Is there any question from the audience? Okay, I have just one. I don't know if you also analyzed the structural integrity of such kind of shapes formed with fib, but do you believe that the strategy may also have an impact on the structural integrity, fatigue strength, crack growth, static strength, whatever?
Yeah, thank you for the question. What I would say is, I think that when the beam, when the ion beam is interacting with a solid, there will be a damage zone into the structure. So, for instance, if you're having a crystalline material, the beams will, the ions, they will come with a high energy, and they will dislocate and disrupt the structure, causing some amorphous zone, and also implantation of ions into your material. So I'm guessing this would probably have an effect if you're making some kind of microstructure using the fib. But then this approach would be beneficial because you can, with this multi-step approach, you could also use a lower acceleration voltage on the beam. In this case, I was just using different beam currents, but you could also change the acceleration voltage, and this would cause much shallower damage in the structure. Yeah.
Okay, thank you. Any other question from the audience? Okay, just one by Professor Torgersen, please.
Thank you very much for this presentation. Do you foresee that with your approach, I mean, these are very untypical geometries, so to say, for this type of process. Would you foresee that you can make structures that are kind of end user parts or kind of electronic parts for a specific application besides just a simple sample preparation for the TEM? And if so, what would you see as potential use cases of these structures?
So the fib is used much for making very special structures, say, as you said, with the TEM, and for making like in situ samples for transition electron microscopy, where you're having electrodes and such. But there are not any good methods that, or it's not that common to make more complicated structures in situ where you're able to have this finish pass approach. So there might be other characterization techniques where that would require both a complex geometry, but also this finish pass that you would, which is easy for TEM lamellas, but difficult for complex geometry. So this is something which is possible with this method, and this is something that I'm also working on with my collaborators at Stanford University in Footprints.
So would you say that this is a kind of a new approach to prototype some MEMS structures, for example?
Yes.
Okay. Thank you.
Thank you, Marcus. We can skip to the next presentation, which is given by Amir Ardeshiri Lordeiani from Politecnico di Milano. The presentation is entitled A Comprehensive Numerical Framework to Study the Effect of Process Parameters on Cold Spray Coating and Additive Manufacturing. Please, Amir, you can start.
Hello, I will start sharing my screen.
Yes.
Okay. All right. Hello again, everyone. I'm Amir Ardeshiri Lordejani, a PhD student at Mechanical Engineering Department of Politecnico di Milano. I'm going to present a study on a comprehensive numerical framework to study the effect of process parameters on cold spray coating and additive manufacturing, which is the result of researches done by me, Professor Sara Baghrifard, Mr. Davide Polzani, and also Professor Mario Guagliano. I'm first going to briefly discuss some of the less covered topics that were missing maybe from my video presentation, and then I will move on with the rest of the presentation very quickly. Well, cold spray, as an introduction, is a solid-state powder deposition method. It is used to deposit small particles of micron scale using a very high speed jet of helium, nitrogen, or air, which propels the particles when passing through the level nozzle. And when they hit the substrate surface, they undergo severe deformations, and as a result, they attach to the substrate. This happens at relatively low temperature, so there won't be any powder melt almost. There is very low oxidation. We can achieve very high densities and also other favorable characteristics. However, there are also some limitations that can be seen here. Cold spray can be used for a variety of applications, such as surface functionalization, protecting the surface from destructive environmental factors, and repairing the in situ damages to the surface of the part, and also additive manufacturing. However, there are some parameters that, like almost any other additive manufacturing method, should be carefully controlled. I'm going to discuss in the presentation the effect of powder size, morphology, velocity and temperature, and also substrate material, presence of oxide layer, and angle of impact. In this presentation, we have two basic models. First one is a single particle impact model, which is a Lagrangian model with the descriptions that can be seen here. And also a CEL multi-particle model, which is used mainly for measuring the effect of the discussed parameters on porosity of the final coating. There is one main factor about our single particle impact, which is considering an enhanced adhesion modeling. In order to do that, we have to break a single particle impact into three separate steps. because we are taking into account additional factors. First, I would like to remind you that in Lagrangian model, you can model different cohesive contacts. In the CL model, the elements that are the parts that are moving through a Eulerian domain are sticky and they adhere to each other. It's unavoidable. So there is almost no way that we can apply a selective cohesion in Abacus. And also in SPH, there are some limitations when we want to SPH or smoothed particle hydrodynamics. There are some limitations because when we want to apply the SPH both to the substrate and the particle to benefit from it. So we selected the Lagrangian model. We start by doing the single particle impact with a very simple contact model, which consists of a normal hard contact, a coefficient of friction for the tangential contact, and also some heat dissipation. However, we are going to include a damage model into the material model to evaluate the damage of different elements, specifically in the particle. We are going to do that because we assume that the adhesion between the particle and the substrate is not going to happen all over the contact area between the particle and the substrate surface. So first, we are going to measure the amount of the damage for the elements on the surface of the particle, specifically the lower surface of the particle that comes into contact with substrate. Then we evaluate the STG or damage index that is provided by Abacus, and we select the elements that have a damage higher than a specific threshold, which is acquired from material properties. Then we adjust the model by adding a cohesive contact between the particle and the substrate. However, we do not apply to all of the particle surface, but we just apply to the elements that have the damage index higher than the set threshold. And we run the particle impact again to achieve a precise impact simulation. Sorry. As I discussed, we are going to apply these two factors. First is identifying the contributing elements in the cohesion and adhesion of particle to the substrate in order to identify a lower threshold for the deposition velocity window of the particle. Because if we consider the particle velocity in cold spray, if the particle velocity is lower than the threshold that we are talking about, then the particles will rebound and there won't be any cohesion, any adhesion, and also any deposition as a result. However, if we increase the velocity above this up to a specific point, we will have successful deposition. And after that point, because of the very high rebounding energy and rebounding velocity and also energy, the cohesion that has been formed between the particle and the substrate will break, and we will be left with just some craters that are formed as the effect of the impact on the substrate and an eroding effect. We talked about how we are going to apply the lower threshold. However, to apply the higher threshold, we are going to add damage also to the cohesive contact interaction model that we have included in the general Abacus model. Here you can see an overview of the algorithm that we follow in order to achieve the enhanced results. And as we discussed, mainly we use two different models. Here you can see a summary of the differences between these two models, namely the Lagrangian model and the CL model. The most important factors are we are going to use almost always 50 particles in the CL model, in the multi-particle impact model. And as I discussed, we cannot enforce any selective cohesion in the CL model. So for the contact, we will always consider a normal contact between the particles and the substrate. The last part that I wanted to discuss is how we are going to control the parameters of the cohesive contact.
Amir, I would suggest to go faster.
Okay.
Since we are running out of time. Okay. Thank you.
Okay. I just wanted to mention that while some of the parameters that we use in the cohesive contact are acquired from some well-known experiments, such as the tensile test at different strain rates, the others are played with until the deposition velocity window is matching the experimental findings. Using this, we discussed different parameters. We found out that increasing the particle size, as is also supported by the experimental results in a decrease in critical velocity of the particle. We also found out that a harder substrate will result in lower critical velocities for a given constant particle material. We also found out that changing the impact angle from 90 degrees or normal state to a more acute angle will result in higher porosity and also a specific change in the shape of the porosities based on the morphology of the particle. The same is also supported by studying a single particle in impact model and changing the impact velocity. We can see that by decreasing the impact velocity, we will need a higher velocity to achieve the cohesion, so a higher critical velocity. We discussed different morphologies, and we found out that, as can be seen, we will need higher velocity to achieve the adhesion for irregular shapes, and we will also have higher porosity for higher irregularity. And finally, in order to identify and study and compare the deformation rate, we defined a new deformation factor, which is defined also in the video. But first, we consider the central cross-section. We calculate the moment of inertia of that, both for the initial shape and also the final deformed shape. Then we calculate the radius of gyration, and we propose a new deformation ratio for irregular shapes by dividing the initial radius of gyration over the final radius of gyration. We also discussed the presence of effective presence of oxide layer, which will result in a higher critical velocity. Thank you for your time.
Thank you, Amir. The presentation was very interesting and nice. I'm sorry, but there's no time for questions. And I believe that if someone is interested in the talk and in the work, can directly contact Amir by email. Okay, yes, thank you, Amir, again. Sorry.
Thank you.
We have to skip to the next presentation, which is given by Alia from the Iran University of Science and Technology. Is Alia present? Okay. The presentation is entitled Optimization of Tensile Properties for 3D Printed PLA Material Using Taguchi and ANOVA Methodologies.
Hello, sir. Can you hear me?
Yes, I can hear you.
Okay.
Please put in, okay, that's perfect. You can start. Thank you.
Okay. I'm Atıf Rajabi, PhD student in Industrial Engineering Department of Iran University of Science and Technology. In recent years, there has been increasing interest in 3D printing technology. Selecting the best possible level for process parameters is one of the greatest challenges. Therefore, we aim to provide insight on the influence of process parameters on mechanical properties of printed parts using design of experiments, actually DOE method. Our presentation was divided into 4 parts. First, I introduced our work, then describe data and optimization methodology, and finally, I mentioned the conclusion. We investigated fused decomposition modeling because of its wide adaptability, simple mechanism, and low cost. Among all materials, we use PLA filament because it's one of the most used materials. And also, we want to study the effect of process parameters on the tensile characteristic. We choose ultimate tensile stress, elongation at brick, modulus of elasticity, yield strength, and toughness as mechanical properties. Also, our printing parameters include infill density, extrusion temperature, raster angle, and layer thickness. And we try to answer this question in this work. Can we achieve the valuable result with fewer experiments? And also, what should we do when the proposed level for experiment for mechanical properties are different? We have a different proposed level. What should we do? So, we can see our printing parameters in this table and their levels. We proposed an orthogonal array with 12 experiments to study the properties of a printed object with 12 tests. In the same work, Liet et al. Manufactured 24 groups of dog bones and tensile test samples made from PLA material to study the mechanical properties. We analyzed their reported experiments. Our first methodology is Taguchi method. It's a DOE method actually. The result can be seen in this figure's graph. This graph shows the result, and you can see the mechanical properties behavior in different level of printing factors. For example, you can see some of them has significant effect. Some of them has positive, and some of them has, for example, negative effect. And according to these effects, we summarize our proposed best level in this table. As you see in this table, for some of them, for example, for this proposed level, we don't know what would be our mechanical properties. And to solve this problem, we use regression models to predict the response values. The response values is our mechanical properties. And also, there is another problem that you can see the proposed level for ultimate tensile, modulus of elasticity, and yield strength are same. But the level for elongation at brick and toughness are different from them. And so we propose that we can use multi-objective optimization method for more investigation. In regression method, we fitted these regression models for each of a mechanical property. This relationship can be used to analyze printing parameters and also predict and optimize the value of mechanical property. And we also use these equations to optimize each of mechanical property in response optimizer in Minitab, and the result is shown in this table. You can see fitted value, CI, actually confidence interval, and PI prediction interval. Fitted value is the predicted value of the mechanical properties. CI and PI propose an interval, but they are different. CI shows interval for the estimation of the true value of the mean of mechanical property, But PI presents an interval for the estimation of a new individual observation, actually. Um, we see in the previous section that we have different proposed levels. We consider, according to consider importance of stress and toughness, we consider these two mechanical properties. We use the regression method, regression models, and upper bound and lower bound of our printing parameters to form this optimization problem. We examine these two properties with NSG2 method because we have two conflicting goals, and this multi-object optimization method are coded in MATLAB, and the results are shown in this figure. And the result is part of bound that propose a set of solutions that are not dominated, and these non-dominated solutions that are different alternatives that help decision makers to review different choice and select the appropriate values. Actually, it means you can choose between this solution set for any desired preference and possible conditions. If there are other constraints, you can consider them in this model and make your own optimization problem. In sum up, in this work, we show that we can achieve valuable results with fewer experiments. It helps us to save time and cost. Moreover, we show that if there are conflicting results, we can use meta-heuristic, for example, NSGA2 or other meta-heuristic methods or algorithm to help decision makers in choosing proper levels. Thanks for your attention.
Thank you. There's time for a very quick question from the audience, if any. Otherwise, we can skip to the next presentation. Thank you again, Alia, and then we can skip to the next presentation, which is which is given by Sanne van den Boon from TNO in Netherlands. And the presentation, please, you have to unshare your screen. Otherwise, we cannot go on. There's a button on the top of the screen. Alia, okay. Unshare your screen. Okay, thank you. So let's go on. The presentation by Sanne van den Boon is entitled Optimization and Redesign of a Structurally Loaded Fused Filament Fabrication Component, Numerical and Experimental Validation. Please, Sanne, the stage is yours. We cannot hear you. Okay, yes.
I don't find that mute button. Okay, thank you for your introduction. I'll give a short summary of my presentation entitled Optimization and Redesign of Structurally Loaded Fused Filament Fabrication Component. I did this work together with my colleagues Sander, Dennis, Etienne, and Juliette. And the goal of this work was to go through the entire workflow of designing an actual component using fused filament fabrication. So we wanted to start with a design, do the numerical analysis, do some optimization on the design, do the manufacturing, and then test the component. And for this, we've chosen the use case of a ladder step. This is a ladder step that is designed for use on a slanted surface. So you can, is my cursor visible? Can you see where I'm pointing?
Yes, we can see.
Good. So this is a design of the ladder step that we're considering. Here you can see half of the ladder step. Here is the symmetry plane. It is simply supported here at the holes because the rope goes through. It's a rope ladder, and it's the back shown here rests against a slanted surface. And here on the location with the purple arrows, there is a prescribed downward displacement. So that's where the foot of the person walking on this ladder step would be. So we've done the analysis of this using Abacus, and we've also created two redesigns shown here on the right. So on the top, we have the original design. It has a uniform infill structure of 30%. And the first optimization of this design that we did is to redistribute the infill. So the outer geometry of the design is kept the same, but we redistribute the infill densities so that it keeps the same mass, but the compliance is minimized, so it's a more stiffer part. And finally, we also do a design where we print it as a solid, so this bottom design does not have an infill, but it is the complete topology is optimized. Both of these optimizations are done using Tosca. And I said here, we want to keep the mass the same. Unfortunately, due to post-processing of the results, both optimized designs ended up being slightly heavier, but as I will show later, they are also a lot smaller, so it's worth it in the end. And then here on the bottom, I show how we modeled the material parameters. So for the solid parts, so that's the wall layers in these top two designs and the entire bottom part, they are printed as a solid, but actually, as you can see here in the micrograph, there is some porosity. There's these triangular holes due to the printing process. So we've used this representative volume element to homogenize the material properties of the solid parts. And also the infill properties, we don't want to actually mesh the entire infill, so we homogenize the infill properties at various densities, and then we interpolate it using a ramp interpolation. So this is also used in the optimization of the infill distribution. So these are the three designs that we've considered. Then for the sample manufacturing and the experimental testing, we have created 3 samples of each design, so 9 samples in total. Here on the top left, you can see the distributed infill design. So you can here clearly see some lower density infill regions and some higher density infill regions at the more stressed parts of the design. Then we've printed them on an ALD machine, and we've used this test setup to experimentally verify the results. And here you can see also the speckle pattern on the ladder step that was used for the DIC measurements of the strains. And so finally, I have a summary of the results. Here on the top left, you can see the DIC strain measurements compared with the numerical simulations. We can see at least like the distributions of the strains are very similar. And then we can also see here in the photos on the top right that the failure modes of the 3 different designs is very different. So the uniform infill design only got a crack here at the middle center. Well, the optimized infill design, actually, a piece broke from the middle part, and that happened for, I believe, 1 or 2 of the samples. And then finally, the optimized design, when it broke, it actually broke in several pieces. So you can see here that due to this better distribution of the stresses, when it actually fails, it fails very dramatically. And then here in the graph, we can see that the optimized design, so the black lines are the uniform infill, the red line is the optimized infill, and the blue line is the optimized topology. And we see that not only are they stiffer than the original design, which is of course what we optimized for, but they are also stronger, which is surprising because that's not what we optimized for. And as in the plenary speaker this morning already said, it's not necessarily always the case that the stiffer design also leads to stronger designs, but in this case it's actually. And then here in the table you can see that although the optimized designs ended up a bit heavier than the original uniform infill designs, the ratio of the load that they can carry with respect to their own weight is twice as high. So it's really a successful optimization. So to conclude, in this work we have done an entire workflow from design to manufacturing and experiments. And we've shown that FFF can be used for structurally loaded components, and topology optimization can be used to create stronger and stiffer designs. Thank you very much.
Thank you, Sanne, for this nice, interesting, nice presentation. Is there any question from the audience? Okay, and there's one from Clarissa Becker, please.
Hello, everyone. Thank you for the nice presentation. I'm actually wondering if you have an explanation for why the topology optimized structure, which has a filled a complete infill, is performing so much better than the optimized infill pattern. Does that have anything to do with the thickness of the infill structures? Is it maybe too thin, or what kind of explanations did you find?
I think that could be one of the explanations. Actually, we have not experimentally verified the homogenized infill properties by themselves. So that would be definitely a next step to look into that. But I think another explanation is that if you look at the geometries themselves, this original design and also the optimized infill really don't utilize any of these spaces. And of course, if you try to bend the beam, it's very effective to place material here. And for the topology optimized design, that all was design space, and it could actually use that space. So I think that's probably the bigger explanation.
Okay, that makes sense. Thank you very much.
Thank you again, Sanne. I think that we can skip to the next presentation, which is given by Sven Overholm from NTNU. The presentation is entitled Optimizing a Gas Diffusion Layer with Mathematically Defined Structures. Please, Sven, if you are present, share your screen and start presenting.
Hello, can you hear me?
Hello? Yes, we can hear you.
Okay. Can you see my screen as well?
Yes, can you put it in the presenter mode, please? That not this one, the other screen.
Sorry.
No.
Okay.
Otherwise, you can start with that.
Yeah. Sorry.
No problem.
No?
Okay. Yes, that's perfect.
Yes.
Okay.
Thank you. Okay.
Start.
Yeah. Okay. So I'm going to present how to optimize a gas diffusion layer with mathematically defined structures. So first off, we need to increase the efficiencies of fuel cells so it can be commercially available. So in my master thesis, I was looking into how we can make the gas diffusion layer better. So first, the gas diffusion layer is main task is to establish a chemical gradient. So we can efficiently diffuse reactants to the catalyst layer and remove a product water from the catalyst layer. It also needs to have low ohmic resistance so it can carry electrons. So how did we do that? To the left, we can see a traditional carbon paper gas diffusion layer. So it's an unstructured grid. And we are proposing to use triply periodic minimal surfaces to optimize for permeability and electron conductivity. So to the right is the four structures we used in this analysis. So upper left is the Schwarzpair beam, upper right is the cubic lattice, and gyroid and Schwarzpair. So here we can see that all these structures are mathematical defined structure that is repetitive and is very good to use when utilizing additive manufacturing. These structures are divided into what we call a solid and a void. In the void, we have the diffusion of water and reactants, and the solid, we have electron transport in the fuel cell. So the workflow from modeling to analysis is we model the structures in a software called topology, and then we transferred the files to Space Claim, where we cleaned up the geometry and patterned, repeated elements to what we call a representative volume element, which is a representative of the bigger picture because we cannot model the whole membrane, the gas diffusion layer. So for the electrical conductivity analysis, we used a current inlet, so you can see on the upper right, and a voltage potential on the other side, and all the can you see my mouse?
Yes.
Yeah, okay, so all the sides are isolated, so there is no electron conduction to the outer elements. So the results are for a given porosity of the structures. We found that the Schwarzpair structure was the best performing structure, followed by the Schwarzpair cubic lattice and Schwarzpair beam. The Schwarzpair had the best electron conductivity because it's have a really uniform area, a cross-sectional area, so it's highly utilized. If we compare the results to traditional gas diffusion layers, we can see that they are much better performing. This is the true plane direction in a traditional gas diffusion layer and in plane direction of a traditional gas diffusion layer. So they are better performing. For the permeability analysis, we used Stokes steady flow with incompressible fluid water, one phase, and a very low Reynolds number, which lets us use no slip boundary conditions on the walls and pressure inlet of 0.01 Pascal and a pressure outlet of 0 Pascal. So basically we are looking at how much water gets through the structures at a given porosity. So the results shows that the Schwarzschild beam is the structure that has the highest probability, and then that's the most water-true. So it should be a good candidate for product removal. Followed by cubic lattice, Schwarzschild, and Schwern-Gehry. So if we compare the results to traditional gas diffusion layers, we can see that the typical gas diffusion layer has a true in-plane probability that can compare to the results of the Schwarzschild beam and cubic lattice. But if you look at the true plane direction, these structures are performing much better. So yes, if we plot all the results in a logarithmic plot, we can see that the crossing point for the traditional gas diffusion layer is here, and in comparison, we can see that for the Schwarzschild beam and cubic lattice, they have a crossing point here, and it has a large potential, giving the probability and electrical conductivity. So this slide shows a few pictures of the electrical conductivity analysis, and we can see that the cubic lattice have all the gray areas here are not utilized to actually conduct current, so they are not utilized. And if you look at the Schwern-Gehry here, we can see that all the volume is utilized, and therefore it conducts electrons much better for the same porosity. For the probability, we can see this is the cubic lattice, and this is the Schwarzschild beam, that the flow lines are not disturbed at all. They are very straight, and the flow is relatively good. If you compare them to the Schwern-Gehry, which is almost helicoid shaped, they are really tortuous path, and obstructed path. And the Schwarzschild have many small flow channels, so we have these restriction points. I think that is it for me today. Thank you for having me. Any questions?
Thank you, Sven. Is there any quick questions from the audience? Okay, if no, thank you again, Sven, for this nice presentation. We have to keep the schedule and go on with the next presentation, which is given by Riccardo Caivano from Politecnico di Torino. The presentation is entitled Top FAT Methodology Implemented in a Commercial Software Benchmarking Validation. Please, Riccardo, unmute yourself and share your screen.
Good morning, everybody. So I'm going to share my screen and the presentation. Okay.
That's right. Okay.
Perfect. So thank you very much for the introduction. I'm going to talk about our research about the implementation of the Top FAT methodology in the commercially available software HyperWorks and the related benchmarking validation. So the initial problem we addressed was the inclusion of the influence of the additive manufacturing process-induced defects within the topology optimization. Indeed, defects hardly affect the fatigue response of the AM parts. Such defects are, for example, those reported here, like pores, cluster of pores, lack of fusions, and others. So the solution initially was an algorithm named TopFat, which was able to use the Murakami model combined with the stress constraint to include this influence of these defects inside the topology optimization procedure and obtain a reliable design. However, an additional problem appeared because the original TopFat algorithm is a 4,000 lines code written in MATLAB. And so even if it's really highly performant, its extendability on real three-dimensional and complex cases can be complicated. So the presented solution wants to overcome this issue and is basically the implementation of the TopFat as a methodology into the commercially available software HyperWorks and the related benchmarking validation. So for example, here I just reported one case, which is the L-shaped beam case. On the left, there is the final topology obtained with the original TopFat algorithm. Instead, on the right, there is the topology obtained within the commercially available software HyperWorks. The topology is quite different, but both are feasible, and so the implementation on the commercially available software has been successful. And that's just a brief presentation of our work, and I'm here to answer any questions you may have. Thank you.
Thank you, Riccardo, for keeping time and for the nice presentation. Indeed, I am one of the co-author, so I would like to ask to the audience to ask some questions, please. Harry Psiodios.
I just want to ask how the defects are predicted. How are defects are included in your model to make the topology optimization?
Okay, perfect. Thank you very much for the nice question. Actually, we take advantage of a numerical model developed by Murakami. And this model basically, sorry, okay, basically the model can predict the defect population based on a statistical model, which is called LEVD, stating largest extreme value distribution statistical model. And there is based on two experimental parameters, which is mu and sigma. After experimentally, these two parameters can be evaluated. These formula, this statistical model can predict the probability of finding a really big defects. And from these big statistically evaluated defects, it is possible to use this second formula, which is the Murakami model, actually. It depends on other factors, such as the final volume of the component with respect to the reference volume, on the hardness, and on other parameters. And it can give as an output a stress limit over the first principal alternate stress, which should not be super 8. And so after we have this stress limit, it is possible to include inside the topology optimization algorithm the limit over the first principal maximum stress, which is this part here. And so if in the final topology, the first principal alternate stress is not superior to the imposed limits thanks to the statistically evaluated probability, the final design could be considered reliable. That's the stream flow of the procedure and how we evaluate the defects and its effect.
Excuse me. Through this methodology, the location of the defects, the possibility of the location of the main defects is determined.
Yes, it is. And if you see here, there is a parameter called C1, which corresponds to the defect location parameters. And so if the defects are considered superficially, it's superior than if the defects is considered as internal, because if it's closer to the surface, it can be more dangerous for the fatigue life of the component. And so basically in all the simulation we did over both in TopFat and in HyperWorks, this coefficient C1 is considered as the most critical. So as if all the defects should be located superficially. And this parameter is roughly 1.4 for the superficially located defects. So this is the parameter which keep in mind the location of the specific critical defect.
Okay, thank you.
Thank you too for the questions.
Next question by Klaus Pedersen, please.
Yeah, so thank you for the presentation. So if I understood this correctly, then basically you have your much more complicated fatigue measure, and then you kind of reduce that one to the maximum first principle stress, which you put a constraint on. So I think out in the literature, there's quite a lot of people just also trying to use similar methods or with sign from misses or something. But often when you're then actually running the full fatigue calculation, then you don't quite get the same results again. So we always see a little bit different correlations between these two. So I wonder in your case, if you run the full fatigue simulation, if you then if you still have a good correlation between the first principle stresses approach and then actually doing something where you have highly non-proportional fatigue loading, if there's still a good correlation of using this just simplified stress measure.
So, okay, thank you very much for the question. It was one of the most critical points at the beginning of this procedure development. And in the end, we decided to start from a really calculative solution. So we decided to put just one limit over the most critical defect under the most critical load. So yeah, we are partially overestimating the final solution. So it's more calculative because we don't have a real history load evaluation. We just keep the most dangerous statistically evaluated defect and the most critical load application. And then we match them to have the worst case scenario. And if the final topology is safe in this final worst case scenario, is surely safe also in other cases. Because if the stress is not higher enough to let a crack propagate from the most critical defects, so the stress isn't enough high to let the crack propagate, the final design is reliable also in the fatigue regime. So that's the initial idea and the problem we guessed. For sure, as you said, maybe probably steps would be like to consider the history load and try to be like more precise in evaluating this step and just don't consider also the worst case scenario as the only one, but just try to reduce the overestimation.
Thank you. Yeah, that's all. Also, I also came to the same conclusion when I did something similar. Yeah, so I agree. Yeah.
Okay, thank you. Yeah, however, it was a really tricky point at the beginning of the of the topology optimization algorithm development. It was really tricky. Yeah.
Thank you again, Riccardo. We can go on with the next presentation. Please unshare your screen, Riccardo.
Yeah, thank you very much, everybody.
The next presentation is given by Alexander Botin from Penn State University. Is Alexander Botin present? Alexander Botin or some of the co-authors is present. The work is entitled Search for Potential Inhibitors of Acid Corrosion of Steel in a Series Trialomethyl 1,3 decatones. Okay, we can skip to the next presentation and leave this one at the end of the session if any of the co-authors is present. So the next one is given by Sergei Panin from the Institute of Strand Physics and Material Science at Tomsk, Russia. The presentation is entitled Design of 3D printed polymeric tribological units made of wear-resistant composite materials based on advanced high-temperature thermoplastic matrices. Please, Sergei, you can start.
Am I audible?
Yes, we can hear you. You can put your presentation in the presenter mode so that.
So you can see my presentation as well.
Yeah.
Okay.
Can you put it? Can you put it in the presentation mode so that we can see it better?
Just a moment. Just a moment. So,
thank you.
Dear Mr. Chairman, ladies and gentlemen, so let me briefly explain the key ideas of our study. And so it will take about 10 slides to roughly describe the problem and our results. So I'm going to talk about the 3D printed polymeric tribological units. And we used high temperature thermoplastic matrices for FDM printing of them. So next slide. Yeah. So the motivation for this study is application of advanced polymeric materials for production of or fabrication of polymeric friction pairs. So in fact, most of the artificial units, if it takes them for as example, so they are currently produced from the metal part and from the polymeric part. So one of them is hard and another is soft. So there are some problems for such a friction or mating pairs since so the polymer is somehow soft and it's not as wear resistible as necessary. So different specialist experts, they offer to use various materials or various mating pairs like ceramic on ceramic or metal on ceramic and so on. So it's also possible, it's also has some advantages, but the key problem for ceramics is a high processability and expensive processability. And it is brittle. But in terms of using polymers, so we can combine also high strength polymers and soft polymers. And in this case, we are looking for manufacturing something like artificial joints where one part is made of soft polymer like ultra high molecular weight polyethylene, and another part is produced from something more hard of high strength, and it might be, for instance, polyester ketone. So besides a medical application or biological application, so this might be efficiently used in machinery in aerospace industry, but for sure there are some limitations when we made two polymers together, and so that is first problem, and that is the problem of tribology. So another problem is related to additive manufacturing of these materials, and it was a part of our research. So here you can see briefly what is a polyester ketone. At the moment, you can find a lot of research on the topic of 3D printing of PEEK, and here you can see it is at the top, nearly at the top of this high performance or ultra high performance polymers. So first of all, because of the high operational temperature, and also because of the high strength. So besides I mean, all the advantages, it has some drawbacks, and one of them is low wear resistance. And to solve this problem, it should be loaded with various fillers, something like solid lubricant, and another are enforcement. So, and at the moment for medical applications, short carbon fibers
are most spread filler for solving such a problem. So another part for this tribological mating is ultra-high molecular weight polyethylene. So it is widely, or it has been widely used for more than 40 years in medicine in mating with metal counterparts coated by cobalt, molybdenum, chromium. But and another problem, it is very difficult to be 3D printed. So, and the problem is it has very low or nearly zero melt flow index. And in this case, it can hardly be processed by fused deposition modeling. That is one of the most spread, popular, and let me say, not expensive technique for 3D printing of polymers. So we solve the problems of 3D printing, and we solve the problems of design the structure and tribological characterization. So here on the right, you see our homemade 3D printer. It is based on fused deposition modeling, and just to compare, since mostly the parts fabricated by additive manufacturing, they possess low mechanical properties in contrast with ones fabricated by, for instance, hot compression. So we make such a comparison study between composites prepared by two different techniques. So here you can see the structure. On the top, it is polyester ketone loaded with 30% of carbon fibers. So the figure in the center, or micrograph in the center, it is hot compression, and we will like it to 3D print the composite with very uniform structure, and so it means. So, FDM is efficient technique for such a processing. On the, at the bottom, you see the micrographs for ultra-high molecular weight polyethylene. So we combine this polymer with polypropylene in the twin screw extruder, and it allows us to have such a uniform structure. And what is more important, it is processable. It might be 3D printed by the FDM. So we made these materials in a friction pair. So first of all, let me show you the mechanical properties. And I would like to say that elastic modulus of our 3D printed composites is, not lower or even higher in contrast with one prepared by hot compression, both for polyethylene and also for polyester ketone. So that is mechanical properties, and then have a look at the results of tribological tests. So we used a pin-on-disc machine, and here on the left, it is friction coefficient. You see data for friction pair for dry sliding, for tribological conjunction made by hot compression, and this one is for 3D printing. So in terms of friction coefficient for dry sliding, we have low friction coefficient. And if to use some lubrication like water or synovial liquid, you see the friction coefficient is very low for both types of specimen fabrication. And also what is very important for us, so we didn't register anywhere in case of 3D printed specimens. That is for water lubrication, and this one is for dry sliding. For sure, we have some heating, we have some somewhere, but it is mostly related to heating of polymers, because they are, they have very low heat conductivity. And the only problem to solve, the only way to solve this problem is to use water lubrication. That is, that is solved in the human body by the use of synovial liquid. So that is, I mean, that was the result for tribological test, and at the moment we have developed, I mean, the technique for simulation via processes. So you see the preliminary results, and we developed the technique for design of the composites using, I mean, the technology for building a response surface. And you see, I mean, we take the composition as from the center from this area. So that is our idea, that is some of our results, and we hope, I mean, the paper on this topic will be published in a couple of months. So it is, I mean, we are completing writing this material. So it seems that that is it for my presentation, and I'll be glad to answer your questions. Thank you.
Thank you, Sergey, for your nice and interesting presentation. Is there any questions from the audience? If no one, I have just one quick question. You use two kinds of manufacturing processes. Did you find any significant effect on the strength and stiffness related to the manufacturing process, fused deposition modeling or hot pressing?
Okay, so when I mean we take the hot compression as a reference technique because I mean the density is very low. I mean the process for sintering and for crystallization is very stabilized, and so we can form the structure as the best structure and also to achieve the best properties. So then we try to repeat, we try to obtain the same kind of properties and structure under FDM. And as a rule, it's not so good as for hot sintering. But in this case, what is the advantage of FDM? So because of the hot crystallization, we can have something like quenching. And so it is similar for metals, and also it can happen for polymers. It might be related to oxidation. It might be related also for, just for fast, low time of the process. So for this reason, instead of increasing high strength or stiffness, so instead of having it for, because of perfect structure, so we obtain such a properties because of the peculiarities of FDM. So for this particular reason, we are, we can talk about achieving probably 90, 95 or even 100% of the properties that we obtained under hot compression. And also it's not optimized by infill, or it's not optimized by, for instance, we use Taguchi as well for optimization of FDM, but even for our preliminary tests. So we are very close to such a high properties. So now we are going to study, to optimize the weight fraction of the fillers, and we hope it also gives us improvement in properties.
Thank you. That's clear. Professor Torgersen, I think that you can leave your question for directly contacting Sergey. Okay, we can skip to the last presentation of this session. Please, Sergey, and share your screen so that we can keep on.
Just a moment.
Yeah. Yes.
Yeah.
Thank you. That's okay. Okay. The next presentation is given by Professor De Jesus from the University of Porto. The presentation is entitled "Numerical Modeling and Prediction of Residual Stresses in IEC 316L and nickel I-18 nickel 300 steels produced by selective laser melting." Please, Abilio, you can start.
Yeah, good morning, everyone. Can you listen to me?
Yes,
No?
we can see and hear you.
Nice. So, well, first of all, I would like to refer my team that was involved in this research. So, which is about numerical modeling. The presentation I will perform now, or a short presentation, I'd say, but it involves other, components of the research, mainly residual stresses measurement that were already presented in a previous presentation by Marcus. And also we will have another presentation this afternoon by another collaborator of mine, which will talk about well, the properties measurement for additive manufacturing maraging steel. So this work is about numerical modeling of residual stresses, and for this work we have well, select some existing simulation tools in order to get some predictions, and then we are trying to validate the predictions using measurements on residual stresses using X-ray diffraction and also some distortions. We are talking of the laser powder bed fusion process, and we have selected two geometries for the research. The first one is a simple geometry, which is a prism using a very common material in additive manufacturing, the 316L steel. And for this, we added the information about the process, and also we picked from literature some mechanical, well, thermomechanical properties. A second case that was selected for our research is these kind of bridges, which were inspired by the NIST from the National Institute of Standards and Technology from the USA. So, and in this case, we well, printed this material using maraging steel and using our own properties for the thermomechanical behavior of the material. And we also, besides the residual stresses measurements, for this second case, we also perform some deflection analysis. So this bridge can be, after production, can be the pillars, the columns of the bridge could be cut, and we can measure this deflection on the top of the bridge. Regarding simulation approaches, we are in our group testing different approaches. Namely, we start with the more traditional inherent strain approach, which comes from, well, I'd say from welding, well, the simulation, and this technique, well, is the faster one. Because it skips the thermal analysis. However, results could be interesting regarding the deformation, but the residual stresses seems to be not properly evaluated using this technique. So we move on, and now we are working on this weekly coupled thermomechanical analysis, which is composed on two stages of analysis. We start with a thermal analysis. We build the workpiece following the thermal heat input and the boundary conditions, and afterwards we perform the structural analysis, taking into account that thermal history on the workpiece. There are also strong coupled thermomechanical analysis. However, those solutions are very time consuming, and for the moment we are not yet working on this point. For the weekly coupled thermomechanical analysis, we are using Abacus, which has the complete thermomechanical model implemented. And for the heat source, we are using the Goldak, special distribution of heat. So Using this approach, we can activate elements layer by layer. Each layer is activated simulating the recoating process, and then we have the heat source following exactly the same laser path over the powder. In this picture, you are seeing just some random selected time steps, but actually the model integrates all the story of the laser. However, the thermal analysis and mechanical analysis are split in two parts. Regarding the experimental details that were already present to you this week, we analyzed the surface of this prism according to this matrix of points using X-ray diffraction techniques. And so we are now, I will show you results on the surface. We have more data in the deep direction, but it was not yet considered in this validation procedure. And we can see here also the material deposition parameters that were considered in the simulation. Regarding the bridge, this is a picture of the bridge, and we measure the residual stresses on the top of the bridge. After that measurement, we cut the pillars and we measured the distortion or the displacements on these dots on the top of the bridge. So quickly going to the results, we did some parametric analysis, and one important one was about the mesh density. So we start with some rough meshes, as you can see on the right, but soon we understood that this could influence significantly the results. So we need to produce refined meshes, even taking into account, even leading to very significant computation times, like sometimes we may have 1 week of computation time in order to get some results. So anyway, we can see here for the top surface of the prism, some convergence on the stresses, longitudinal and transverse stresses. Afterwards, I can show you some results. The results that I am showing to you are present without any tentative to use or to hide any bad results. So I would say, in general, the results were satisfactory, taking into account the challenge which is this kind of simulation. So in this slide, we can see some results for the prism on the top, and you can see that on the right, the transverse stresses are very accurate predicted. However, for the longitudinal stresses, numerical results over predicted the experimental results. I would say that in these simulations, we consider the base plate fully clamped on the lower bottom surface, which probably would lead to higher stiffness and would have higher impact on the residual stresses, mainly on the longitudinal direction. Then we can see here the stresses on the side surface. And in this case, I'm showing the vertical stresses, which I would say, okay, they are not perfect, but as it seems that we are going better in the predictions as we go away from the interface between the block and the plate. Anyway, I think there is still some room for improvements in the simulations, but I think that these results are anyway encouraging to go in some improvements. Finally, I have some results on the this side surface, smaller side surface, and you can see here some convergence between numerical and experimental results, despite some deviations in some locations, mainly, as I told you, near the interface. Regarding the bridge, the challenge is higher because the geometry is no longer so simple. So in this case, the mesh size will have a very significant impact. We try harder to have very fine meshes, but the computational times sometimes becomes forbidden. Anyway, for a reasonable mesh size, we were able to get some good predictions for the residual stresses in the central part of the bridge. For the longitudinal stresses, which are more important when we want to predict the distortion of the bridge. Regarding the distortion, we can say that the predictions were very much accurate, excluding this extreme point where we underestimated the residual stresses. Anyway, it seems that I think I have finished. Okay, have automatic time for the presentation. So you can see here how we did the measurements. So we cut with the wire cut technique the pillars of the bridge. So and we measured the before and after that cut the geometry of the bridge, and so we got the distortion, and we have here a very good indication of the distortion. So we were very pleased about this. So in terms of final comments, I would say that this is still ongoing process. We are working on simulation. This is one of our topics. One key issue would be to be more precise on boundary conditions. And I think another point that is very relevant are the material properties that are not easy to get, but we are also working on that in that field in order to have the complete thermomechanical properties for some additive manufactured materials, as it is the case of the merging steel. Later on, I think at 2 o'clock, you can see one presentation about the merging steel properties evaluation. Thank you very much.
Thank you, Abilio, for this very interesting presentation. Okay, we have just one question from Harry Psychoios, please.
And at the beginning of your presentation, you've mentioned that you used 3 modeling approaches: inherent strain method, weakly coupled, and strongly coupled. But on your results, I didn't see any comparison of these 3 methods.
Yeah. Actually, we did the inherent strain approach, and we have also this weakly coupled approach. We didn't work on the strongly coupled thermomechanical analysis yet. And regarding the inherent strain, we have some results. Actually, they will be presented in the procedure structural integrity paper. We decide to include. We decided to exclude it from this presentation because actually they were very not so good regarding the residual stresses. They overestimated the residual stresses in 1 order of magnitude. That was not so nice for us to see those results. We have been working on that, try to understand if there is any mistake, but we understood that it is what the simulations are giving. So those results will be presented in the procedure structural integrity paper together with the weakly coupled. So residual stresses are, in my opinion, not nicely predicted using that inherent strain approach.
How do you
distortion? Yeah.
How do you
distortions? We may have some agreement, but not for the residual stresses.
Okay. Did you use lumped layers on weakly coupled thermomechanical analysis?
Sorry, can you repeat? Long layers?
Did you use lumped layers? Layers that
No. In this case, we use layer by layer simulation, which took a long time simulation. But we, in this case, don't use the lumped layers simulation.
Okay, and my final question is regarding the inherent strain approach. How did you determine the initial strain that is the basis for the inherent strain method?
Yeah, that's one question, very interesting. I'm not sure if we have, if I have the answer to you, because this was performed by my collaborators. I'm not sure if George Gil is available at this session and could help. Otherwise, we can tell you later about that.
There's no problem. I just want to ask to clarify my...
Yeah, but I see we can send you later. Let me just... so what is your name, please?
My name is Harry Psycholios.
Okay. So
I will be in contact with you if I...
Yeah. I will try to send you later answer for this question. Okay.
Okay.
Okay. Thank you.
Thank you.
Thank you again. I think that we have to conclude. If Alexander Botin is not present to recover his presentation. Is Alexander Botin present? No? Okay. I think that we can conclude. Thank you again to all the presenters for keeping in time and to the audience for the active participation. It's time now to have lunch for everyone, and let's meet again from the next session at 2 p.m. Have a nice day. Bye.
Bye.
Bye.